The Kawasaki Ninja H2R is built inside one of the most advanced motorcycle factories in the world. From forged engine parts and precision machined frames to carbon fiber panels and hand-polished finishes, every step is engineered for higher speed and power. Today we take you inside the Kawasaki factory to see exactly how the Ninja H2R is made from raw materials to finished superbike. The story of an H2R does not begin on the assembly line. It begins much earlier, within the metallurgical divisions and materials labs that prepare the raw constituents of the motorcycle's essential components. At this initial stage, the journey starts with a block of high-tensile steel alloy, specifically formulated for the H2R's trellis frame. This isn't ordinary steel. Kawasaki engineers design the alloy composition to maximize tensile strength while balancing torsional rigidity and ductility. Sheets and tubing are delivered to the fabrication facility in precisely measured cuts, each one traced through an internal lot tracking system for complete traceability. Within the factory, the raw frame tubing undergoes cold drawing, a process that pulls the steel through dies to fine-tune its dimensions and surface integrity. Cold drawing is chosen specifically because it preserves mechanical strength while yielding tight dimensional tolerances, which are critical for the trellis frame's intricate geometric structure. Robotic armatures position each steel tube beneath automated laser cutting heads that slice the tubes into exact segments, using CNC-defined angles to ensure proper laser fitment during welding. The accuracy here is staggering. Deviations beyond 0.1 millimeters trigger alerts in the system, halting the production cell for inspection. These cut tubes are then transferred via automated conveyors to a robotic frame welding station. Unlike mass-market motorcycle frames, the H2R's frame is entirely hand-welded, albeit with robotic support for fixturing and alignment. Skilled technicians, each trained for months on frame-specific geometries, perform manual TIG welding to fuse the chromoly steel components together. This welding process isn't just about joining metal. It's a delicate operation, balancing thermal input and cooling rates to avoid internal stress or warping, which could compromise high-speed stability at over 300 kilometers per hour. Once the frame is assembled, it enters a dimensional verification stage utilizing 3D laser scanning. The scanning head, mounted on a 6-axis robotic gantry, creates a digital twin of the physical frame, comparing it to the original CAD model within fractions of a millimeter. If the frame passes all checks, it moves to a powder coating line where it is electrostatically coated and oven cured at controlled temperatures. The specific gloss and hardness of the black frame coating are chosen for both heat resistance and resistance to rock chips and vibration-induced wear. Meanwhile, in another section of the plant, the supercharged engine, the beating heart of the H2R, begins its life in the engine assembly hall. This hall is a restricted environment, temperature and humidity controlled, and acoustically insulated from the rest of the plant. The reason is simple. The inline 4-cylinder engine that powers the H2R is not just another power plant. It's an ultra-high performance 998cc unit, force-fed by a centrifugal supercharger capable of spinning at up to 130,000 RPM. Such precision demands a sterile, meticulously maintained production environment. Engine block castings arrive from Kawasaki's dedicated foundry, having been machined to spec using 5-axis CNC centers. These blocks are inspected using ultrasonic resonance techniques to detect subsurface anomalies that cannot be seen visually or through surface scanning. If the casting passes inspection, it is mounted onto an engine cradle fixture, and the first stage of assembly begins. The installation of crankshaft bearings. Each bearing shell is hand micrometered and color-coded marks are applied to designate their oil clearance class. This step is crucial because the H2R engine tolerances are far tighter than in commuter bikes. The goal is minimal oil film thickness for maximum responsiveness without inducing friction-related failures. After the bearings are installed, the forged steel crankshaft is delicately lowered into the block. This crankshaft, balanced to aerospace-grade tolerances, is laser etched with its unique serial number for tracking and quality assurance. Next, titanium connecting rods and forged pistons are assembled offline on dedicated piston rod mating benches. Each piston is weighed and matched to its rod to within 0.5 grams to ensure uniform reciprocating mass balance. Piston rings are installed using rotary ring expanders that ensure even pressure and no deformation. The piston assemblies are then inserted into the engine block using hydraulic-assisted ring compressors, and the crankshaft is rotated by hand through a flywheel fixture to ensure smooth, unimpeded movement. Even the tiniest resistance would be flagged as an indicator of misalignment or contamination. Once the bottom end is secured and torqued in a cross pattern using digitally calibrated torque wrenches, attention shifts to the cylinder head. The H2R cylinder head is a complex component, machined with pent roof combustion chambers, large titanium valves, and dual overhead camshafts. Valve springs are installed using a pneumatic valve spring compressor, and valve lash is adjusted using precision shims measured to within hundredths of a millimeter. Camshafts, hardened and micro-polished, are mounted on journal caps and rotated to align with timing marks on the crank. The timing chain, a double roller unit, is fed through a guide channel and connected to the crank sprocket, then tensioned using a hydraulic chain tensioner preloaded with assembly oil. Once aligned, the engine is rotated again by hand, and valve timing is confirmed using a laser cam phase analyzer that calculates exact intake and exhaust overlap degrees. Now comes the installation of the supercharger, the defining feature of the H2R. The supercharger is assembled in a separate clean cell. Its impeller, machined from a single billet of aluminum, is balanced using high-speed spin balancers before being mounted to the planetary gear drive. The planetary gear unit, in turn, is gear-driven from the crankshaft and is fitted with helical cut gears to reduce noise and increase torque handling. Once mated, the entire supercharger is tested in a closed-loop bench system, where it is spun up using a drive motor to simulate load and airflow output. Only if it meets the volumetric efficiency thresholds is it approved for installation onto the engine. As the supercharger is bolted onto the engine using a dedicated torque fixture, the entire power plant assembly is now ready to move to the dyno test cell. But before that happens, it's moved to a pre-test station where all fluids are filled: high-temperature synthetic oil, long-life coolant, and a special break-in fuel blend optimized for seating piston rings under load. The engine is then mounted into a test cradle wired with sensors and bolted to an eddy current dynamometer. Here, engineers run the engine through a programmed break-in cycle, gradually increasing load and RPM while monitoring combustion pressure, knock, oil pressure, and temperatures. Each engine must meet specific power output metrics before it's allowed to leave the test cell. For the H2R, this figure is over 310 horsepower, measured at the crankshaft. Engines falling short are automatically rejected and moved to a forensic diagnostics bench where engineers determine whether the issue lies in fuel delivery, boost pressure, valve timing, or internal mechanical components. Once the dyno-tested engine has passed all performance and durability checks, it is removed from the test cradle and placed onto a specially designed rolling engine dolly. This dolly is more than a simple transport mechanism. It interfaces with hydraulic lift systems, allowing technicians to tilt, raise, and lower the engine precisely for the upcoming frame integration process. Before reaching the frame marriage station, however, the engine is routed through a pre-integration checkpoint where a technician conducts a final surface inspection, verifying all sealing surfaces, torque marks, and component connections. At this stage, all auxiliary components, such as the alternator, starter motor, oil cooler, and coolant hoses, are pre-mounted to reduce complexity during frame insertion. Meanwhile, the painted and fully inspected trellis frame, already cured and cooled from its powder coating process, is mounted on an assembly jig at the chassis preparation station. Here, the steering head bearings are greased and installed using an automated bearing press that ensures equal pressure distribution to avoid warping or damage. Into this steering head, the forged aluminum triple clamps are inserted and torqued to specification using a digital torque wrench with data logging capability. The handlebar mounts are temporarily attached for alignment purposes, but the handlebars themselves will come later in the line. At the engine marriage station, the prepped engine and trellis frame are brought together. A hydraulic lift slowly raises the engine into position beneath the frame, while two alignment pins guide the engine mounting points into perfect register with the frame brackets. 4 titanium bolts, lighter and stronger than traditional steel, are inserted and torqued in a diagonal sequence to avoid any stress concentrations. This step marks the true structural birth of the motorcycle. From this point onward, the machine is no longer a collection of parts. It is a unified mechanical system. With the engine mated to the frame, the motorcycle chassis is now placed onto the primary assembly line, an overhead conveyor system that moves each bike along a guided rail through multiple semi-automated workstations. The first station is the front suspension installation area. The H2R utilizes massive 43mm KYB AOS2 forks, which are fully adjustable and coated with a low-friction DLC layer. Each fork is filled with a precise volume of high-performance suspension oil using a vacuum fill station, then sealed and compressed to check for internal leaks. Once ready, the forks are inserted into the triple clamps and aligned using a digital laser alignment rig to ensure perfectly parallel orientation. Following this, the front wheel assembly, which consists of a Marchesini forged aluminum rim, dual 330mm Brembo discs, and a Pirelli Slick racing tyre, is rolled up to the workstation. The wheel is mounted onto the axle, and the Brembo M50 monoblock calipers are installed with anti-vibration shims. The brake lines are routed along the fork legs using pre-formed clips, and each banjo bolt is torqued and marked with a color-coded paint pen for visual confirmation of completed steps. Parallel to the front suspension assembly, another robotic cell is preparing the swing arm sub-assembly. The H2R's single-sided swing arm is a hollow, forged aluminum unit with internal stiffeners. It is laser welded and then machined to accept the axle carrier and chain adjusters. Once verified for alignment using a 3D measurement gantry, the swing arm is connected to the frame using a solid pivot bolt, then connected to the rear shock. The rear suspension is a gas-charged KYB monoshock unit, also fully adjustable, and mounted on a rising rate linkage system for progressive damping under heavy loads. With front and rear suspension in place, the H2R is now a rolling chassis capable of supporting its own weight. At this point, the conveyor system gently lowers the motorcycle onto a rolling dolly with locking casters, freeing up the overhead rail for the next unit. The rolling chassis is pushed manually to the next station, the electronics and wiring harness integration bay. Unlike lower-tier motorcycles, where wiring is often installed as a single unified harness bundle, the H2R employs a modular wiring system. Multiple sub-harnesses for the engine control unit, traction control system, data logger, ABS system, and dashboard are installed independently, with each module having its own waterproof snap lock connector. The main harness is routed through the spine of the frame, secured with P-clips and thermal-resistant sleeves to protect from engine heat. Each connector is scanned using an RFID tool to ensure proper mating, and the system performs a low-voltage continuity check before proceeding. Once the electrical systems are routed, the control units are mounted in their designated locations. The inertial measurement unit is mounted beneath the seat. The ECU is housed in a vibration-isolated tray behind the headstock, and the quick-shifter sensor is attached to the gear linkage rod. The dashboard, a full-color TFT display, is installed into the carbon fiber front cowl support and wired into the CAN bus network. With control systems in place, the next stage is the installation of the fuel system. The H2R's fuel tank is not merely a container, it is a shaped aluminum shell with internal baffles and foam inserts designed to reduce sloshing during extreme cornering. Each tank is pressure tested at 1.5 times normal operating pressure to check for leaks. A high-flow fuel pump is mounted internally, and the tank is lined with a corrosion-resistant coating that protects against ethanol degradation. The tank is installed onto rubber isolators on the frame spine and connected to the fuel rail via quick disconnect couplings. Underneath the fuel tank, the intake system comes together. The airbox is a sealed high-capacity plenum chamber designed to handle pressurized air from the supercharger. It features a ram air intake duct and a high-flow air filter made from synthetic fibers. Sensors for intake air temperature and pressure are inserted, and the throttle bodies, ride-by-wire, electronically controlled units, are bolted directly to the intake ports. The supercharger outlet feeds directly into the airbox, and a blow-off valve is installed to regulate excess pressure during throttle closure. Once all intake and fuel connections are secured, the exhaust system is installed. The H2R utilizes a titanium exhaust header that is hand-welded and purge-welded from multiple conical sections. Each pipe is flow bench tested prior to assembly to ensure even back pressure across all 4 cylinders. The exhaust system includes a collector and a short, undertail silencer, designed to reduce weight and maintain optimal power output with minimal restriction. Sensors for oxygen content and exhaust temperature are threaded into the headers and linked to the ECU. At this point, the bike is fully assembled mechanically, but bodywork has not yet been applied. That comes in the next segment of the production process. But before that, the motorcycle moves into the first startup and diagnostic bay. Here, technicians connect a master diagnostic tablet to the ECU via the OBD port. The system runs a full checklist, verifying sensor functionality, fuel pump pressure, throttle actuator operation, and system voltages. Once verified, the bike is started for the very first time. This initial start is a tense and critical moment. The technician listens closely for any abnormal mechanical noise, monitors the idle speed, checks for warning lights on the TFT display, and ensures that oil pressure rises immediately upon startup. The engine is allowed to idle until it reaches operating temperature, during which time the cooling fan, radiator circulation, and combustion balance are all evaluated. Any deviation from spec prompts an immediate stop and transfer to the diagnostic cell for further investigation. If the startup test is successful, the motorcycle is shut down and moved to the fluid leak test station. Here, a UV dye is added to the oil and coolant systems, and the bike is placed under black light to reveal any possible leaks at hoses, joints, or gaskets. Pressure is applied to the cooling system using a sealed radiator cap rig, and the oil system is pressurized via a pneumatic pump. This ensures that even micro leaks are detected before the bike proceeds to final cosmetic assembly. With all functional systems now tested and verified, the powertrain mounted, the electronics integrated, and the fluids checked for sealing integrity, the Kawasaki Ninja H2R is finally ready to receive what many consider its most striking feature, its full carbon fiber bodywork. Unlike plastic fairings found on standard motorcycles, the H2R's aerodynamic surfaces are crafted entirely from pre-preg carbon fiber panels that are formed, trimmed, and finished in a tightly controlled composites facility within Kawasaki's aerospace division. Each carbon panel, from the sculpted front cowl to the aggressive side fairings to the single-piece tail section, begins life as a sheet of carbon fiber impregnated with epoxy resin. These sheets are hand-laid into CNC machined aluminum molds, layer by layer, with careful attention to fiber orientation and overlap. This layup process determines the final strength and stiffness of the component. And technicians follow a digital blueprint showing precisely where each ply must be placed. Once the layup is complete, the mold is vacuum sealed inside a heat-resistant bag and placed into an autoclave. In the autoclave, the part is subjected to high temperature and pressure, curing the resin and fusing the carbon plies into a single monolithic shell. The process takes several hours, during which the exact pressure and thermal cycle are carefully controlled and logged. After curing, the mold is cooled and the part is demolded and sent to the trimming station. Here, 5-axis CNC water jet cutters remove excess material and create mounting holes, while laser measuring arms verify dimensional accuracy down to fractions of a millimeter. Once trimmed, each body panel goes through a polishing and surface inspection process. Technicians in cleanroom suits buff the surface to prepare it for paint, but for the H2R, this isn't just a cosmetic paint job. It's a defining visual signature. The entire carbon shell is sprayed with Kawasaki's proprietary mirror finish paint, a multi-layered formula that gives the H2R its iconic black chrome look. This paint contains a layer of silver-infused base coat that reflects light like a mirror, followed by multiple layers of clear coat that are wet sanded and polished between applications. The painted carbon fiber parts are then cured in low dust ovens at carefully controlled temperatures. When they emerge, they undergo final inspection under polarized lighting to reveal any imperfections invisible to the naked eye. Only when each piece passes this inspection are they released to the final cosmetic assembly line. Back in the main assembly hall, the rolling chassis is now stationed at the fairing installation bay. Here, a team of 2 technicians works on each unit, using soft-gloved hands and non-marring tools to install the carbon fiber bodywork. The upper cowl is mounted first, secured to a lightweight subframe using vibration-resistant fasteners. The side fairings follow next, installed with grommeted bolts and lined with thermal insulation on the inner surfaces to protect against engine heat. The winglets, a defining aerodynamic element of the H2R, are bolted to the sides of the front fairing using precision jigs. These carbon fiber strakes generate downforce at high speeds and are carefully aligned to match the factory's computational fluid dynamics models. The tail section, which includes the seat pan and integrated rear lights, is installed last. It slots over the subframe like a precision machined cover, secured with hidden fasteners that leave the outer surface clean and uninterrupted. The final visual pieces include the windscreen, made of high-impact acrylic formed over a heated vacuum mold, and the mirrors, which are unique to the H2R in that they are replaced by aerodynamic blades due to its track-only designation. These aerodynamic devices further contribute to the overall downforce and high-speed stability of the motorcycle. With all external components now in place, the motorcycle advances to the lighting and display verification stage. Even though the H2R is not street legal and lacks conventional headlamps, it still features essential lighting systems for track use, including brake lights and dashboard illumination. A diagnostic terminal is connected once more to the onboard electronics, which triggers all LEDs, signal displays, and digital readouts. Any pixel dropout or timing issue in the TFT display is immediately flagged, and the dashboard is swapped out before the motorcycle proceeds. The next phase is torque auditing. Using a handheld digital wrench interface, a technician rechecks every critical fastener on the motorcycle, referencing a torque database specific to the H2R. Each bolt, from the engine mounts to the suspension linkages to the brake calipers, is checked, and the data is wirelessly transmitted to a central quality control server. This system creates a complete torque audit trail for every unit, ensuring that no component is under or over-tightened, which could lead to safety issues under track loads. Following torque audit, the motorcycle is moved to the final mechanical verification bay, a rolling road dynamometer enclosed in a safety chamber. Unlike the earlier engine dyno test, this test evaluates the entire drivetrain system, including wheel alignment, chain tension, gearbox operation, and traction control responsiveness. The motorcycle is strapped down securely onto a rotating drum, and a technician rides the bike through a simulated series of track laps using paddle inputs to shift gears, apply throttle, and trigger braking. The onboard IMU and traction control system are monitored in real time to assess how the electronic aids respond under aggressive load transitions. One particularly crucial part of this test is the quick shifter evaluation. The H2R uses a bidirectional quick shifter that allows for clutchless upshifts and downshifts under load. The dyno software simulates various throttle and RPM combinations while the technician triggers shifts. Sensors measure delay time between shift input and gear engagement, and the ECU adjusts the ignition and fuel cut profile dynamically. If lag or false neutrals are detected, the quick shifter sensor or shift drum is re-inspected. Following dyno verification, the motorcycle is shut down and allowed to cool under controlled airflow. It is then cleaned using ionized air to remove any dust or debris collected during testing and rolled into the inspection corridor, a quiet, well-lit area reserved for aesthetic and dimensional verification. Here, trained inspectors examine every square centimeter of the motorcycle's surfaces under fixed-angle lighting rigs that highlight reflections and contours. They check for paint consistency, panel fitment, fastener flushness, and emblem placement. The final inspection is concluded with a checklist signed by a master inspector who holds clearance to certify H2R units for packaging. A QR-coded certification tag is applied beneath the seat, containing digital records of every test, torque, spec, and visual check the motorcycle has passed. This tag remains with the bike for life, accessible by service centers and authorized Kawasaki technicians. At this point, the motorcycle is ready for crating and shipping, but before that occurs, a factory photographer captures high-resolution images of each unit for archival and legal purposes. These photos document the visual condition at the time of shipment and are stored alongside each VIN's production history. The H2R is then rolled into the final staging area, a climate-controlled packaging room where each motorcycle is carefully enclosed in a custom-built steel and wood crate. The front wheel is braced, the suspension compressed slightly with straps, and the bike is cocooned in protective foam. Every surface prone to scratching is wrapped with a low-tack film. Accompanying the motorcycle is a documentation pack that includes a certificate of authenticity, a technical user manual, a tuning guide, and the special tools required for trackside maintenance. Now ready for departure, the crated H2R is scanned into the logistics database and scheduled for dispatch. Its destination could be a private collector's garage, a professional racing team's paddock, or a high-end performance dealer specializing in exotic motorcycles. Once the Kawasaki Ninja H2R has been crated and logged into the factory's outbound inventory system, its journey through the global supply chain begins. The finished motorcycle, now nestled inside a reinforced steel-tubed crate with engineered shock absorption inserts and padded contact points, is not treated like standard inventory. This is not mass-market production. Each unit is registered and scheduled for delivery with the same level of care typically reserved for aerospace-grade cargo or high-value prototype machinery. The H2R crate is fitted with a tamper-evident seal and a GPS-enabled tracking unit. This small battery-powered device is embedded in the crate frame and continuously broadcasts location, temperature, and shock readings throughout the duration of the shipment. The goal is absolute transparency and control. Kawasaki's logistics division uses a centralized tracking portal to monitor every H2R in transit, ensuring that any anomaly, a sudden temperature spike, an excessive tilt angle during forklift handling, or an unexpected deviation from a scheduled route triggers a real-time alert and investigation. Within the Kawasaki factory's outbound logistics terminal, all outgoing H2Rs are staged in a secure area awaiting carrier pickup. This area is isolated from regular shipping docks and utilizes biometric access controls. When transport is scheduled, only certified freight handlers are permitted to load the crated bikes onto specialized trucks equipped with air ride suspension systems. These vehicles reduce vibration and road shock that could otherwise stress the precision-fitted carbon components or delicate electronics inside the crate. Each transport vehicle is assigned a specific destination hub, most commonly one of Kawasaki's global distribution centers. These hubs, located strategically in Europe, North America, the Middle East, and Asia, are more than just warehouses. They are hybrid facilities combining bonded customs zones, climate-controlled storage, and dealer preparation stations, all operating under strict quality assurance protocols. When a truckload of H2R units arrives at one of these hubs, the unloading process is supervised by Kawasaki regional logistics managers. Each crate is inspected for seal integrity and then scanned into the regional inventory management system using the embedded RFID and QR codes. For units destined for overseas markets, international freight forwarding is used. Crates are loaded into secure ISO shipping containers fitted with humidity control packs and shock-damping floor mounts. These containers are then booked onto cargo ships under insured, high-priority manifests. During ocean transit, the environmental monitoring systems embedded in the H2R crates continue logging data, which is uploaded via satellite uplink every 12 hours. When the containers reach port, customs clearance is expedited through Kawasaki's import-export licensing system, which pre-registers each motorcycle's VIN with the appropriate government authorities to simplify the paperwork associated with limited use non-street legal vehicles. Once the motorcycles arrive at their respective dealer prep centers, they are again moved using air ride trucks and secured holding bays. The dealer-level uncrating process is perhaps one of the most sensitive moments in the entire chain. These centers are equipped with padded flooring, overhead cranes, and specialized unboxing stations designed specifically for ultra-high performance motorcycles. Each crate is disassembled manually, using torque-limited tools to avoid overstressing any fastener. The protective wrap and foam buffers are removed, and a technician conducts a full visual inspection before any mechanical interaction occurs. At this point, the motorcycle is still in a semi-dormant state. While fully assembled at the factory, the H2R is shipped with several systems disabled or set to low activation mode. For example, the ECU is placed in a transport-safe state to prevent any unauthorized ignition or tampering during transit. The traction control system and launch control features are also disabled until activation codes are entered through the factory diagnostic tablet. These codes are provided only to certified Kawasaki race dealer technicians who have completed a specialized training program exclusive to the H2R platform. The first step during dealer prep is to activate the motorcycle's electrical systems. A lithium-ion high-output battery, which was shipped separately to avoid power drain or risk of damage, is installed using a torque-calibrated battery tray mount. The diagnostic tablet is then connected, and the technician runs a software handshake that reactivates the ECU, initiates a full sensor sweep, and calibrates the electronic throttle bodies to their neutral closed position. This is followed by a firmware update if required, ensuring that the bike is running the latest version of Kawasaki's proprietary control logic, an intricate blend of traction, wheelie, slide, and launch control algorithms designed for elite track use. Fuel is then added to the tank, typically a high-octane, ethanol-free race blend sourced by the dealer. This ensures consistent combustion characteristics for the first startup under the dealer's supervision. The cooling system is topped off with pre-mixed long-life coolant, and brake fluid levels are checked. While all systems were previously pressure tested at the factory, this step ensures that nothing has been compromised during transport. The first dealer-level ignition is performed under controlled conditions. The motorcycle is mounted on a paddock stand with wheel chocks and exhaust ventilation systems in place. The technician initiates the ignition cycle, monitors the startup process, and allows the bike to idle while all systems reach operating temperature. During this time, the technician observes engine temperature, oil pressure, throttle responsiveness, and warning indicators. Once warmed up, the throttle is blipped to ensure proper response from the supercharger system. A high-pitched whine confirms that the planetary gear-driven supercharger is spinning freely, and boost sensors are checked to verify pressure increase under transient throttle input. Next comes dynamic system calibration. The dealer technician enters a closed test loop menu via the diagnostic interface, and the motorcycle performs a series of controlled internal tests. These include throttle plate synchronization, IMU pitch and roll calibration, wheel speed sensor checks, and brake pressure modulation trials. These diagnostic steps ensure that all ride assist systems are correctly aligned and functioning before the motorcycle is released to the client. Before final delivery, cosmetic detailing is performed. The bike is cleaned using non-reactive anti-static cloths and waterless detailing sprays to preserve the mirror finish. Tire pressure is adjusted to the recommended range for track delivery, and chain slack is fine-tuned based on the factory's specification under rider weight simulation. The data logging module, if the customer has opted for the full telemetry package, is also installed at this stage, including its GPS antenna and onboard SD card reader. At this point, the motorcycle is ready for customer delivery, but the H2R is not simply rolled out onto the sales floor. In most cases, the delivery is either performed at a private unveiling event or within a dedicated performance showroom, often involving customer briefings, technical walkarounds, and personalized instruction. The purchaser receives a digital service log, a registration keycard for the diagnostic system, and, depending on region, a certificate of ownership detailing the motorcycle's serial number and place of manufacture. Some customers even receive a titanium plaque etched with their VIN, engraved at the factory using the same fiber optic laser that marks engine components. For customers intending to race the bike, additional services are offered. These include initial track setup, suspension tuning based on rider weight and intended circuit, and ECU mapping optimization. Kawasaki certified race engineers are sometimes deployed directly to high-profile clients to help integrate the bike into a team's racing fleet or private collection. In total, from the moment an H2R begins its life in the alloy preparation bay to the moment it is fired up in a client's garage or paddock, the process spans multiple continents, dozens of specialists, and a series of rigorously enforced quality checkpoints. No step is accidental. Every decision, from the type of crate to the orientation of the brake lines during shipping, is designed to protect and preserve the uncompromising nature of the Ninja H2R. Before any assembly begins on the factory floor, months of design and configuration have already taken place through digital modeling and client collaboration. Scania offers thousands of configurations, from cab types and engine sizes to axle arrangements and emissions profiles. Every order is configured down to the most minute specification using proprietary software systems that feed directly into the production planning systems of the factory. This digital integration ensures that each vehicle is built precisely to customer requirements, and it sets the stage for the just-in-time production model that Scania factories are known for. The process truly begins at the component level, starting with the chassis frame, the very skeleton of the truck. These frames are not formed on-site at every assembly plant. Rather, they are usually manufactured at specialized Scania facilities, such as the one in Oskarshamn, Sweden, which is renowned for its advanced laser welding and robotic bending capabilities. The raw material used is high-strength structural steel, delivered in coiled sheets or cut plates from steel mills. These sheets undergo multiple forming processes, including automated press bending, where robotic arms position the steel under immense pressure to form the longitudinal beams that serve as the base of the truck frame. After initial shaping, the steel beams enter a sophisticated robotic welding line. Here, computer-controlled robotic arms move with choreographed precision to apply dozens of welds to each frame component. Each welding head is equipped with sensors that monitor temperature, pressure, and seam alignment in real time. This ensures not only the structural integrity of the frame, but also guarantees a level of repeatability and strength that simply cannot be matched by manual welding. After welding, the frames undergo surface cleaning using shot blasting, a process that fires small steel pellets at high velocity to remove mill scale and other surface impurities, leaving behind a clean, textured finish ideal for powder coating. Next comes the anti-corrosion treatment, which is absolutely vital given the operating environments that Scania trucks face globally. The prepared frame is dipped into large immersion tanks containing anti-corrosive coatings. These coatings bond to the steel surface and offer long-term protection against rust and environmental wear. Once coated, the frame is cured in high-temperature ovens to ensure the treatment hardens properly and maintains adhesion through the vehicle's life cycle. While chassis frames are being processed, the cab structure, the cockpit of the truck, is being built in parallel. Scania's cab production is typically handled in highly automated body shops. The core of the cab begins as pressed steel panels that are stamped into shape using massive hydraulic presses. Each press can apply hundreds of tons of force, transforming flat sheet metal into complex structural elements like roof panels, side walls, and floor pans. These pressed panels are then moved by robotic arms into positioning jigs where they are tack welded together to form the basic cab shell. The welding of the cab shell is another highly automated process. Industrial robotic arms, fitted with multiple welding torches, navigate around the jig to apply hundreds of spot welds with exacting precision. Sensors track the positioning down to millimeter level tolerances, ensuring every cab structure is perfectly square and secure. As with the chassis frame, once the cab shell is fully welded, it is subjected to shot blasting and anti-corrosion dipping. After treatment, the cab shell is baked in industrial curing ovens and then passed into the next phase, painting. The painting process is one of the most visually striking steps in the factory. Trucks are typically painted in customer-specific colors, and Scania's paint shops are designed to switch colors rapidly with minimal waste. First, the cab shell enters a cleaning station, where it is rinsed, degreased, and coated with a phosphate layer to promote paint adhesion. Next, it enters the electrocoating tank, a large bath filled with a water-based paint solution that is electrically charged. The cab is submerged and an electrical current is applied, causing paint particles to bond electrochemically to the metal surface in a uniform layer. This electrocoat layer is corrosion resistant and acts as a primer for the top coat. Once cured in an oven, the cab shell enters the color booth. This area is a climate-controlled environment where automated paint robots, guided by 3D scanning systems, apply base coat and clear coat layers with astonishing accuracy. The robotic arms mimic human wrist movements, but with far more consistency and speed. Depending on the finish, additional layers like metallic flakes or special high-gloss coatings may be added. After painting, the cab passes through a final curing oven, where the coating is hardened under controlled heat conditions. While the cab and chassis are progressing through their respective lines, work begins on the engine, the heart of every Scania truck. Scania is known globally for manufacturing its own engines, and the engine assembly takes place in facilities with a near-surgical level of cleanliness. Engine blocks arrive from foundries where molten iron has been cast into precisely machined forms. These blocks are cleaned, inspected, and then sent through CNC machining lines to be drilled, bored, and honed. Critical components like cylinder bores, oil channels, and mounting faces are machined to micrometer level tolerances to ensure proper sealing and performance. The engine assembly line is a hybrid of human craftsmanship and automated precision. Components like the crankshaft, camshaft, pistons, and connecting rods are assembled using semi-automated workstations where torque-controlled tools tighten bolts to exact specifications recorded in a central database. Scania engines are known for their modularity. Many of the components can be shared across different engine variants, simplifying logistics and repair. Each engine is assembled in stages, with sensors and barcode tracking, ensuring that every step is validated before moving to the next station. Once the engine is fully assembled, it moves to the hot test cells, where it is connected to a computerized test rig and run under simulated load conditions. These test cycles verify oil pressure, emissions output, power delivery, and temperature control. The engine must pass every parameter before it is certified for installation. Failures are extremely rare due to the high degree of automation and quality control earlier in the process. By this stage in the production process, the frame, cab, and engine are all nearly complete. The next phase is the main assembly line, a linear path where all major components are brought together. This line stretches hundreds of meters through the heart of the factory and is divided into dozens of stations, each with a specific responsibility. Trucks move along the line on large powered platforms or guided vehicles, allowing workers and robots to access all sides without repositioning. The first step on the assembly line is the chassis outfitting, where the bare steel frame receives mounting brackets, fuel tanks, air tanks, electrical conduits, and brake lines. Each part is pre-assembled into kits that arrive from sub-assembly areas and are bolted on using torque-controlled tools. Workers scan every part's barcode into the digital tracking system, ensuring complete traceability from installation to delivery. As the chassis assembly progresses down the main line, the stage is set for one of the most critical moments in the truck's birth: the installation of the drivetrain. This includes the mounting of the engine, transmission, clutch assembly, and propeller shafts, all aligned and fitted with micrometer precision. The engine, having already passed its hot test, arrives at the drivetrain installation zone pre-mounted on a subframe cradle. This subframe allows the engine to be maneuvered easily and with extreme accuracy. Overhead, automated hoists fitted with dynamic positioning systems gently lower the engine into the frame rails. A laser-guided alignment system ensures that the engine mountings perfectly match the pre-fitted brackets on the chassis. At this point, technicians, supported by robotic arms that hold the engine weight, secure the mounting bolts using calibrated torque wrenches. Every bolt torque is recorded and logged digitally to create a traceable quality certificate tied to the vehicle's serial number. Following engine installation, the gearbox, a heavy and complex component, is hoisted into position behind the engine. Scania often uses its own automated manual transmissions, which integrates seamlessly with the engine via a robust clutch assembly. The clutch mechanism is pre-aligned with the flywheel, and the entire transmission unit slides onto guide pins with barely a millimeter of clearance. Here, technicians connect the hydraulic lines, gear linkages, and electrical connectors that allow for automated gear shifting, engine brake interaction, and adaptive cruise functionality. With the drivetrain in place, attention turns to the rear axle and suspension systems. Depending on the truck's intended use, long-haul, construction, or specialized applications, different axle configurations are applied. Some trucks feature a single rear axle, while others utilize tandem configurations or even additional tag axles. The axles arrive pre-assembled from Scania's axle plant, complete with brakes, hubs, and suspension linkages. They are lifted into place by hydraulic jacks and bolted to the chassis with spring packs, air bellows, or hydraulic suspension systems already integrated. Next comes propeller shaft installation, connecting the transmission to the rear axles. These shafts are balanced dynamically at the supplier's facility to prevent vibration. Universal joints are fitted with greased couplings and protective covers, ensuring long-term durability under high torque loads. At this point, the foundation of the truck's powertrain is complete. However, without electrical and pneumatic systems, the vehicle would remain lifeless. The next station handles electrical harnessing and air system integration. Scania trucks feature an extensive network of electrical harnesses, connecting everything from the engine control module and dashboard to rear light clusters and sensors. These harnesses are laid out in custom configured looms that match the specific vehicle configuration. Workers unroll and clip these looms into pre-installed brackets along the chassis rails, securing them with fasteners and protective sheathing. The plugs and connectors are then checked for correct mating, and a low-voltage continuity test is performed to validate the integrity of each circuit. In parallel, technicians install air hoses and pneumatic control lines, crucial for the operation of brakes, suspension, and gear shifting systems. Scania uses color-coded hoses for easy identification: blue for service brakes, red for emergency lines, yellow for auxiliary systems. The hoses are pressure tested before installation and connected to manifold blocks fitted with quick-release couplings. Once in place, the entire pneumatic system is subjected to a leak-down test using compressed air. Pressure sensors monitor the rate of decay, and if it exceeds a predefined threshold, technicians isolate and rectify the issue before the vehicle proceeds. With the chassis now wired, plumbed, and powered, the moment arrives for the cab to be mounted. The painted and primed cab shell, now fully treated and cured, has been proceeding through a parallel line where interior components are added. Before it is even lifted onto the chassis, the cab undergoes pre-fitting of the dashboard, insulation, wiring, and climate control systems. The dashboard arrives as a single pre-wired module complete with instrument cluster, infotainment unit, control switches, and HVAC ducting. It is installed into the cab using a robotic arm that slides the assembly into its predefined slots and secures it with vibration-resistant fasteners. At this stage, seats, pedal boxes, steering columns, and interior trim pieces are installed by skilled technicians. Each element is configured based on customer preferences, from seat fabric and placement to storage compartments and auxiliary switches. Once the interior is complete, the cab is transported via an overhead conveyor to the cab marriage station, a precise and dramatic point in the assembly process. Here, a massive cab lifting robot equipped with multi-axis movement positions the cab above the chassis. Using laser alignment sensors and pre-programmed coordinates, the system lowers the cab onto 4 chassis mounting points. Pneumatic mounts or mechanical bushings are inserted to dampen vibrations and provide ride comfort. Once seated, high-strength bolts are applied with synchronized torque tools, and the cab becomes one with the chassis. Following this, technicians connect the main wiring harness and pneumatic lines from the cab to the chassis, a process known as cab-chassis interface. These connections include CAN bus data lines, power feeds, brake system controls, and auxiliary switches. As soon as these connections are complete, the vehicle is able to wake up electronically for the first time. A diagnostic tablet is plugged into the OBD port and the truck performs a systems check. Any discrepancies or error codes are logged and addressed before the truck moves forward. The vehicle now advances to the fluid filling and commissioning station. Here, all essential fluids are added, including engine oil, coolant, transmission fluid, brake fluid, power steering fluid, AdBlue, and diesel fuel. Each fluid fill station uses metered pumps that log exact fill quantities and pressure levels. Automated sensors inside the engine and tank systems confirm that fluid levels are within range before proceeding. Once filled, the truck moves to the initial startup station, where the ignition is switched on for the first time on the line. The starter motor cranks the engine, which should come to life smoothly. A team of technicians monitors engine performance, checking for warning lights, irregular noise, or leaks. The air compressor charges the brake system, and all pneumatic circuits are tested for function. This includes pressing the brake pedal, triggering the parking brake, and cycling the air suspension. Next, the truck undergoes a dynamic rolling road test inside a fully enclosed test chamber. The vehicle is driven on rollers that simulate real-world road resistance, while various systems are tested under load. This includes acceleration tests, ABS brake tests, gear shifting patterns, cruise control behavior, emission system feedback, and traction control activation. The data is streamed in real time to diagnostic software, where engineers verify that the truck operates within all calibrated parameters. Upon passing the rolling test, the truck is driven into the final inspection bay. Here, inspectors conduct a detailed walk-around, checking for cosmetic imperfections, paint defects, missing trim pieces, or loose fittings. Each headlight, indicator, fog lamp, and brake light is checked for functionality and alignment. Mirrors are adjusted, windscreen wipers tested, and all cabin electronics, including navigation, air conditioning, radio, and USB ports are verified for operation. Once the final inspection is complete, the vehicle moves to the finishing line, where customer-specific decals, model badges, and optional accessories like bull bars, sun visors, or additional lighting rigs are added. Every Scania truck is tailored to its owner's vision, and this station gives each one its unique identity before it leaves the factory. The completed truck now rolls into the validation and delivery area, where all data from the manufacturing process, component serial numbers, torque values, diagnostic results, and inspection records are compiled into a digital certificate of compliance. This certificate accompanies the truck throughout its life, acting as a birth record for servicing and warranty purposes. At this point, the truck is technically complete, but its journey is far from over. In the next section, we will follow how Scania handles post-factory logistics, transport, dealer preparation, and delivery to the end customer, along with insights into technological innovations and modular production strategies that continue to shape Scania's dominance in global trucking. Once the truck passes its final on-site validation and is cleared for delivery, it enters a new phase in its life cycle: post-factory logistics and outbound handling. This transition is just as carefully orchestrated as the build itself. A Scania truck may be fully assembled, tested, and polished, but before it can reach the customer, it must navigate a labyrinth of post-production processes, including staging, transport planning, documentation handling, and final handover preparation. This stage marks the convergence of manufacturing precision and supply chain excellence. The first step in this process is vehicle staging, which occurs in a designated outbound yard adjacent to the factory. This outdoor staging area is organized with military-grade precision, divided into zones based on delivery destination, vehicle type, and shipping method. Trucks are driven, not towed, from the final inspection area to the appropriate staging bay. Each vehicle is equipped with temporary wheel covers and protective wraps over vulnerable surfaces like mirrors, windshields, and chrome trim. These protective measures prevent damage during transport, especially when trucks are carried on open trailers or cargo vessels. In the outbound yard, every truck is again scanned using RFID and barcode systems, confirming its identity and correlating it with a live logistics management system. This software tracks all trucks awaiting dispatch and organizes them according to optimal shipping schedules. Depending on the final destination, a truck may be routed for domestic road delivery, loaded onto a rail car, or prepared for maritime shipment if it's headed overseas. Each route comes with its own handling protocols. For domestic deliveries within Europe, trucks are often driven under their own power by certified logistics drivers. These drivers, trained in Scania vehicle systems, are responsible not only for transportation but for monitoring the vehicle en route. Before leaving, they perform a second round walk-around inspection, checking fluid levels, tire pressures, and verifying that the truck matches its shipping manifest. Each journey is GPS tracked and time logged, ensuring total visibility for the customer and Scania's distribution center. If the truck is destined for international export, the logistics become more complex. Vehicles headed for distant markets like South America, Asia, or Africa are transported in batches, often using ro-ro vessels, or roll-on/roll-off ships. Prior to shipment, trucks undergo a pre-export treatment. This includes draining fuel to a minimum safe level, checking emission systems to meet port regulations, and applying additional weatherproofing layers to vulnerable components. If local regulations require specific emissions calibrations or market-specific software updates, these are applied at this stage by an outbound technician using a portable diagnostics tablet. Trucks bound for shipping are driven onto specialized transporters and secured with heavy-duty wheel chocks and tie-down systems. These transporters then carry them to port terminals, where logistics partners manage loading onto ro-ro decks using low-speed maneuvers to protect drivetrains. Throughout this entire handover process, every movement is tracked, and a digital chain of custody is maintained. In some cases, vehicles are not shipped fully assembled. For certain regions with import restrictions or high shipping costs, Scania employs a CKD strategy, complete knockdown. In this method, trucks are partially disassembled after factory completion and packed into containers, then shipped to regional assembly centers. Here, local teams reassemble the trucks under supervision, with full adherence to Scania's engineering and quality standards. This allows Scania to maintain a global footprint without needing a full manufacturing line in every country. Back in Europe, however, trucks that remain in their final configuration are delivered either to regional logistics hubs or directly to dealerships, depending on customer contracts. These logistics hubs serve as a final buffering point before customer delivery. Here, each truck is cleaned again, checked for any transport damage, and in some cases, fitted with market-specific accessories like tachographs, radio equipment, or fleet telematics systems. These are often added just before delivery to ensure compliance with local transport laws or client specifications. Once the vehicle reaches a Scania dealership or customer depot, a final pre-delivery inspection, or PDI, is conducted. This check is performed by certified dealer technicians who cross-reference the vehicle's production history with a detailed checklist covering all operational systems. This includes cabin electronics, tire and wheel torque, headlight alignment, climate control operation, door seals and warning systems. Any required updates to onboard software, such as navigation databases or telematics modules, are downloaded and installed. At this point, the truck is nearly ready for handover to the customer, but Scania doesn't simply hand over the keys. For fleet clients or first-time buyers, a dedicated Scania delivery specialist may conduct a full walkthrough of the truck systems. This includes explaining the adaptive cruise control functions, emergency braking systems, lane departure warnings, engine braking modes, and fuel-saving strategies. Drivers are often given a demonstration of how to use Scania's onboard telematics system, known as Scania Fleet Management, which allows fleet operators to monitor fuel consumption, driver behavior, vehicle health, and maintenance schedules in real time. This entire process, from component welding to client delivery, is only possible due to the extraordinary level of digital integration within Scania's production and logistics ecosystem. Every part, process, and movement is connected through a unified IT platform that synchronizes planning, inventory, production, and outbound delivery. This digital backbone allows Scania to offer mass customization at industrial scale, which is rare in heavy vehicle manufacturing. Beyond the sheer logistics of delivery, what truly sets Scania apart is its modular architecture, a production strategy that deserves closer inspection. Unlike many truck manufacturers that rely on rigid product lines and bespoke configurations that increase complexity, Scania uses a tightly controlled system of shared components and scalable designs. For instance, the same type of engine block can be used across multiple power ratings, with changes in turbocharging, fuel injection mapping, or transmission pairing creating different performance profiles. Cab shells also share mounting points, crash structures, and roof lines, with final variations created through bolt-on panels, interiors, and accessories. This modularity dramatically reduces the number of unique parts required on the factory floor, streamlining logistics and reducing time between customer order and vehicle build. It also ensures that spare parts are widely compatible, simplifying aftermarket servicing and reducing downtime for fleet operators. For Scania, modularity is not just a design choice. It is a strategic manufacturing philosophy that underpins everything from tooling and robotics to workforce training and dealer support. Inside the factories, this approach enables a high degree of automation. Robotic systems handle repetitive, precision-critical tasks such as welding, painting, and component fastening. Yet the human role remains central, especially in final assembly, inspection, and troubleshooting. Scania invests heavily in worker training, with programs that teach technicians how to read digital work instructions, use torque validation tools, and interpret real-time diagnostics data from vehicles in production. These skills are critical in maintaining quality across a product range that offers nearly infinite customization. To further enhance efficiency and quality, Scania has implemented smart factory technologies, including IoT sensors embedded throughout the production line. These sensors monitor equipment status, production flow, and product quality in real time. If a robotic welding arm shows signs of drift, or if a torque gun applies a value slightly out of spec, the system alerts supervisors instantly. Predictive maintenance algorithms analyze these data streams to prevent unplanned downtime, allowing equipment to be serviced before failure occurs. Sustainability is another cornerstone of Scania's manufacturing model. The company has made major investments in reducing the environmental impact of its facilities. This includes using renewable electricity, water recycling systems in paint shops, and closed-loop material recovery processes. For instance, steel offcuts from cab panel stamping are collected, sorted, and returned to suppliers for reprocessing. Paint overspray is captured and filtered before it reaches the atmosphere, while heat generated by curing ovens is recycled to warm nearby buildings. Even the logistics fleet used to move trucks from plant to port has undergone greening. Many Scania factories use their own battery electric or gas-powered truck transporters for short-range movements, reducing emissions around the factory campus. Scania's long-term goal is to create a fossil-free value chain, meaning not just fossil-free trucks, but a zero-emissions process behind every vehicle's creation. What emerges from all of this is not just a truck, but a precision-built, software-integrated, environmentally conscious transport machine designed to serve its owner with maximum uptime and minimum operating cost. Every bolt torqued, every panel painted, and every test completed is done with the understanding that this machine will soon be barreling down highways, climbing mountains, or navigating mines, often in the most demanding environments on Earth. And so, as a freshly built Scania truck pulls out of the outbound lot under its own power, fully tested, aligned, and gleaming in its custom livery, it carries with it not just cargo, but a legacy of Scandinavian engineering, lean production mastery, and digital age innovation. As the newly minted Scania truck rolls off the assembly line and onto the road, its journey as a manufactured product may be complete, but its role as a data-rich, high-performance logistics tool is just beginning. What differentiates Scania in the world of heavy-duty vehicles is not just its robust physical engineering, but also the intelligent integration of software and digital systems embedded throughout the truck. These features are not just bolted on at the end of production. They are enabled and supported throughout every stage of the manufacturing process. At the heart of this smart infrastructure is the Scania Communicator, a telematics control unit installed during the cab outfitting phase. This device connects the truck to Scania's fleet management system and remote diagnostics platforms. It functions as a two-way communications gateway between the vehicle and Scania's global network, transmitting real-time data on vehicle health, driver behavior, location, and fuel consumption. While the physical hardware is relatively compact, its installation is incredibly precise. During assembly, technicians route antennae, signal cables, and CAN bus interfaces through pre-designed channels in the cab, ensuring electromagnetic compatibility and resistance to vibration. The communicator's integration enables predictive maintenance, a significant evolution in vehicle lifecycle management. Throughout operation, the truck continuously monitors dozens of performance parameters: oil pressure, coolant temperature, brake wear, turbocharger pressure, emission levels, and more. These data points are compared against factory thresholds, and if any system approaches a condition that could cause failure, an alert is generated. This could trigger anything from a simple driver notification to a pre-scheduled service appointment at the nearest Scania workshop. It is a direct result of a factory design philosophy where the vehicle's digital nervous system is assembled and validated just as rigorously as its mechanical one. Alongside predictive maintenance, the truck's electronic control systems, also installed and configured on the assembly line, provide a high level of operational automation. Modern Scania trucks are built with dozens of ECUs, each responsible for a specific subsystem such as engine management, brake control, transmission logic, and climate systems. These units are connected via a redundant CAN network architecture, which not only increases fault tolerance, but also simplifies diagnostic procedures. During production, technicians use factory-grade diagnostic terminals to flash the appropriate firmware to each ECU, calibrate its behavior based on the truck's configuration, and verify communication across the entire electronic network. Scania's modular philosophy also extends to advanced driver assistance systems, many of which are pre-installed on the production line but activated or configured according to the customer's specifications. For example, the radar sensors used for adaptive cruise control and autonomous emergency braking are mounted on the front bumper during final assembly, precisely aligned to maintain millimeter-level accuracy over the vehicle's life. Similarly, the forward-facing camera that enables lane-keeping assistance is fitted behind the windshield during cab assembly, carefully positioned with a jig to ensure a clear, centered field of vision. Once installed, these components are connected to a centralized ADAS controller, which interprets sensor input and makes real-time driving decisions. These systems are subjected to a suite of calibration and alignment procedures before the truck leaves the factory. On the test track, radar and camera systems are validated against standard reference objects and road markers. In a controlled environment, the truck is driven through a calibration tunnel equipped with reflective targets, road signs, and lane markings designed to simulate real-world conditions. The vehicle's onboard systems must correctly interpret these stimuli, and if any discrepancies are found, technicians adjust sensor positioning or recalibrate software parameters using diagnostic interfaces. The cab interior too reflects a fusion of mechanical craftsmanship and digital design. Every detail, from the curvature of the dashboard to the responsiveness of touchscreens, is a result of ergonomic research and industrial design thinking. Scania recognizes that its drivers may spend days or even weeks living inside their cabs, and thus the manufacturing process treats the interior not just as a workplace, but as a living space. During cab outfitting, highly trained technicians assemble a range of custom options, from sleeper bunks and refrigerators to infotainment systems and integrated GPS navigation units. These elements are delivered to the line in kit form, each kit tailored to the customer's build sheet. Each cab interior is assembled under tightly controlled conditions to minimize dust, moisture, and static electricity, which could interfere with sensitive electronics. Seats are bolted to reinforced mounting points welded into the cab shell during body assembly, and each one is torque checked and height adjusted based on ergonomic templates. Touchscreen interfaces and instrument clusters are plugged into the vehicle's central network and tested via digital loopback to ensure correct display and input functionality. The HVAC system, including its filters, ducting, and thermoelectric units, is pressure tested and leak checked using nitrogen injection methods before being approved for operation. Another layer of sophistication is found in Scania's drive mode management system, also programmed during the production process. Depending on the truck's intended use, long-haul highway driving, urban logistics, construction haulage, or extreme terrain operation, the engine and transmission control units are calibrated to optimize for performance, fuel economy, or torque delivery. These calibrations are not simple throttle mappings. They include dynamic interaction between acceleration profiles, shift timing, exhaust gas recirculation rates, and even cooling fan activation thresholds. Engineers use proprietary software tools during assembly to upload the correct strategy maps into each ECU and then perform a synchronization cycle, ensuring all systems operate under a unified logic framework. In high-performance applications, such as off-road or heavy load logistics, the truck may also be equipped with retarders, differential locks, and terrain modes. These features are controlled by modules installed under the dashboard and linked to the vehicle's main control network. Their installation involves not just physical mounting, but precise firmware configuration and sensor calibration. For instance, the differential lock actuator includes a position sensor that must be zeroed against the axle's true neutral position during installation. Once installed, these systems are tested during the dynamic run phase to ensure they engage and disengage correctly under simulated load. Meanwhile, aerodynamic elements such as roof deflectors, side skirts, and underbody fairings are installed toward the end of the main assembly line. These parts are often lightweight composite materials and are affixed using vibration-dampened fasteners and adhesive compounds designed to withstand high-speed airflow and temperature fluctuations. Their role in fuel economy is non-trivial. Even minor misalignments can increase drag, so final inspection stations are equipped with laser-guided measuring tools to verify exact positioning. Assembly teams cross-check these with 3D digital overlays displayed on large screens at the workstation. Beyond the truck itself, the factory also assembles and configures support technologies such as Scania Zone and Scania Driver Support. These tools are software-based, but rely on correctly installed hardware during production. GPS modules, accelerometers, and vehicle-to-infrastructure communication units. Once activated, these systems allow operators to set geofenced zones, where speed, emissions output, or engine performance is automatically regulated based on environmental or regulatory constraints. All of this logic is programmed through cloud-based platforms, but it depends entirely on the integrity of the installation work completed on the factory floor. Scania's embrace of digitalization also includes its end-of-line analytic systems, which collect every data point recorded during the truck's production. These include sensor calibrations, fluid fill quantities, software versions, torque readings, and test drive results. Once the truck completes its final quality checks, all this information is compiled into a digital build certificate, stored in Scania's central server network. This certificate not only proves the vehicle's compliance with legal standards, but it also becomes the backbone for future updates, diagnostics, and warranty assessments. Because of this meticulous build documentation, over-the-air updates can be rolled out to Scania trucks even after they have left the factory. The communicator module facilitates this functionality, allowing engineers to deploy firmware improvements, bug fixes, or performance upgrades without requiring the truck to return to a service point. This capability, made possible only because the production process embeds software management from the beginning, is rapidly becoming a key differentiator in the world of commercial transport. Perhaps most impressively, all of this technological complexity is achieved without sacrificing modularity, durability, or long-term serviceability. That's because every element, from wiring looms and ECUs to cab panels and control switches, is installed with future maintenance in mind. Harnesses are routed through accessible channels, ECUs are mounted in service boxes, and diagnostic ports are placed in standardized locations regardless of configuration. This consistency allows Scania dealers worldwide to service a wide variety of truck models with a common toolset and shared training, reducing cost and maximizing uptime for operators. The sum of all these innovations, from embedded sensors and adaptive software to modular electronics and digital infrastructure, is a Scania truck that operates not merely as a mechanical platform, but as a living, communicating system capable of learning, adapting, and reporting throughout its operational life. This vision of the modern truck as a responsive and evolving tool is deeply rooted in the manufacturing philosophy that builds it. A philosophy where every bolt, sensor, and wire is installed with purpose, tested with rigor, and documented with precision. Behind every meticulously crafted Scania truck lies a vast, highly organized human and mechanical ecosystem, an integrated workforce structure combined with world-class lean production methodologies. These systems are designed not only to uphold the brand's legendary quality standards, but to continuously improve them, model after model, day after day. While the end product might be steel, rubber, glass, and code, the beating heart of Scania's manufacturing process is its people and the smart systems they use. Scania's factory workforce is divided into several highly specialized roles, each optimized for a specific part of the assembly line or manufacturing process. These include welders, material handlers, electronic assembly technicians, test engineers, paint technicians, quality controllers, and logistics coordinators, among others. However, what truly distinguishes the Scania workforce is not rigid job segregation, but a dynamic cross-functional approach. Many workers are trained across multiple disciplines and encouraged to rotate tasks, which fosters a deeper understanding of the entire truck building process and enables agile response when production demands shift. This flexibility is essential because Scania operates under a pool-based production system, a fundamental component of its lean manufacturing strategy. Rather than producing trucks in large batches based on forecasted demand, Scania builds each truck to order, with every unit reflecting a unique customer configuration. When a client places an order, that request propagates through Scania's production planning system, triggering a cascade of component manufacturing, subassembly preparation, and final assembly scheduling. Every workstation on the line is updated with this incoming configuration data in real time, enabling the workforce to prepare for exact variations even before the chassis reaches their station. To manage this complexity, Scania employs a cell-based manufacturing layout, particularly in cab and engine subassembly. In this model, small autonomous teams, called production cells, take full ownership of assembling specific components or systems. Each cell is responsible not just for assembly, but also for quality control, minor maintenance of their equipment, and implementing continuous improvement initiatives. Workers within these cells hold daily stand-up meetings to review performance metrics, quality issues, and improvement suggestions. These meetings are an embodiment of Scania's commitment to Kaizen, or continuous incremental improvement. This improvement philosophy is not left to chance. Scania empowers its workers with structured frameworks like the Scania Production System, a variant of the famed Toyota Production System, adapted for the unique challenges of modular truck manufacturing. SPS is built around key principles like right from me, demand-driven flow, and standardized work with flexibility. Each station has visual boards displaying production targets, current throughput, quality alerts, and safety metrics. Any worker, at any time, can pull an andon cord, a signaling mechanism that immediately halts production to address a problem or anomaly. Far from being penalized, such actions are encouraged, reinforcing a culture of quality ownership. SPS also ensures that work instructions are standardized and digitized. At every station, touchscreens provide step-by-step guidance for each unique truck configuration, including diagrams, torque settings, part numbers, and even short instructional videos. This system ensures consistency, even when different workers or shifts are involved. It also supports the introduction of new model variants or upgraded parts, as digital updates can be rolled out instantly across the entire facility. But the factory's brain doesn't stop at the workstation level. Scania's facilities are organized using advanced logistics and material replenishment systems. These include just-in-time and just-in-sequence delivery models. In the JIT approach, components arrive at the assembly line exactly when needed, reducing on-site inventory and waste. JIS takes this a step further by ensuring that parts not only arrive on time, but in the exact order the assembly line requires them, matching the customer-specific build schedule. To make this possible, Scania utilizes autonomous guided vehicles and collaborative robots, also known as cobots. AGVs are programmed to navigate specific paths throughout the facility, transporting parts, kits, and tools from storage to workstations. These mobile units are equipped with obstacle detection sensors and onboard computers, allowing them to safely navigate busy factory environments and prioritize urgent deliveries. Cobots, on the other hand, work directly alongside human operators. They handle tasks like component positioning, torque application, and small part assembly. Because cobots are designed to operate safely around people, they can perform repetitive precision tasks while allowing human workers to focus on complex decision-making and quality assessments. One of the most advanced implementations of lean philosophy at Scania is its digital twin system. This virtual representation of the entire truck assembly process allows engineers and planners to simulate workflows, test layout changes, and even trial new product designs in a fully digital environment before committing changes to the physical factory floor. These simulations integrate real-world production data, making them incredibly accurate and predictive. Before a new model is introduced, it is built and validated in this digital environment, ensuring the tools, workstations, and instructions are perfectly prepared for real-world production. The importance of training and workforce development cannot be overstated in this high-performance environment. New employees go through comprehensive onboarding programs, including virtual reality training simulations, where they practice assembly techniques and safety procedures in a risk-free setting. More experienced workers have access to continuing education through Scania's in-house training academy, which covers topics such as electronics diagnostics, sustainability practices, robotics programming, and leadership development. These programs ensure that Scania's workforce remains adaptive, skilled, and deeply connected to the company's long-term goals. Scania's commitment to sustainability extends well beyond the trucks it produces. It's embedded in the very operations of its factories. Each manufacturing site is governed by a green production strategy, which includes aggressive targets for energy efficiency, waste reduction, and carbon neutrality. Solar panels line the roofs of production buildings, and in several sites, geothermal energy or district heating is used to manage interior climate control with minimal environmental impact. Water used in paint shops and testing areas is filtered and recirculated using closed-loop systems, reducing freshwater usage dramatically. Waste from steel stamping, machining, and welding operations is meticulously sorted and sent back to steel suppliers for recycling, creating a circular materials economy. Even the packaging used for inbound components is standardized and reusable. Suppliers ship parts in containers that are returned, cleaned, and reused repeatedly. Scania's internal logistics fleet, used to move materials between factory sites and distribution hubs, now includes electric trucks and vehicles powered by biofuels, reducing the carbon footprint of interfacility transport. Each of these sustainability initiatives is audited and quantified, with progress reported in annual sustainability disclosures. The factories themselves are certified to international standards such as ISO 14001 for environmental management and ISO 50001 for energy management, ensuring that improvements are not only achieved but institutionalized. These practices aren't just good for the planet, they're good for production. Energy-efficient lighting, heat recovery systems, and smart building automation lower operating costs, which ultimately contribute to Scania's competitive advantage in manufacturing. Moreover, by reducing the environmental footprint of its operations, Scania aligns itself with the increasingly stringent regulatory demands in global markets, ensuring compliance without last-minute adaptation or retrofitting. But lean and green aren't the whole story. Scania also embraces operational transparency and external collaboration. Factory tours are not uncommon, not just for public relations, but for academic, industrial, and supply chain partners. These visits are carefully choreographed but open in intent, demonstrating Scania's willingness to share best practices and invite scrutiny. Likewise, feedback from suppliers, service technicians, and even end users is fed back into the production process. If a common failure mode or service complaint emerges from the field, engineers collaborate directly with line workers to trace root causes and implement corrections, sometimes within days. This culture of bottom-up innovation is rare in large-scale manufacturing, but thrives at Scania. Workers are encouraged to submit improvement suggestions, known internally as yellow cards, through a structured feedback mechanism. These ideas can range from tool redesigns and safety enhancements to procedural changes that save time or reduce fatigue. Implemented ideas are celebrated in team meetings, and successful contributors are rewarded not just with recognition, but often with career advancement opportunities. The ultimate outcome of all this is a manufacturing operation that is resilient, adaptable, and deeply human-centric, despite the heavy use of automation and digital systems. Each truck, though shaped by machines and moved by algorithms, bears the unseen fingerprints of hundreds of skilled individuals who have each left a mark on its creation. It is a deeply collaborative process where man and machine act not in opposition, but in orchestration. The production of a Tesla vehicle begins long before any car takes shape on the assembly line. Deep within the vast expanse of a Tesla gigafactory, a meticulously orchestrated sequence of processes brings together raw materials, robotics, and human ingenuity to transform aluminum, lithium, silicon, and countless other elements into one of the most advanced electric vehicles on the planet. From the first bolt of sheet metal to the final pixel on the touchscreen interface, every component is born of a vision rooted in automation, precision, and sustainability. We begin with the raw materials that will ultimately form the structural skeleton of the car. Aluminum coils. These massive, industrial-grade aluminum rolls are delivered to the stamping facility in pre-cut widths and are carefully inspected for thickness consistency, surface finish, and chemical composition. Tesla predominantly uses high-strength aluminum alloys for many of its structural components due to their lightweight yet durable properties. These alloys are crucial to achieving Tesla's performance goals without sacrificing efficiency or safety. As each coil is unspooled, it is fed into a massive blanking press, a machine capable of cutting large sheets into specific dimensions called blanks. These blanks, often the size of a car door or hood, are prepped for the stamping process, where one of the most visually dramatic parts of the car's creation takes place. The stamping area, often housed in its own building due to the sheer vibration and noise, is where enormous dies, precision-engineered molds weighing several tons, shape these blanks into panels that will form the body-in-white structure of the car. Each die is lowered into a stamping press, often a servo-driven press with forces exceeding 5,000 tons. These machines exert immense pressure in milliseconds, forming the aluminum blank into complex geometries. Multiple stages of stamping may be needed for a single panel, including draw, trim, pierce, and flange operations. After stamping, robotic arms lift and transfer the formed panels onto conveyor belts, directing them to a quality inspection zone where laser scanners and human inspectors check for warping, stress marks, or micro cracks. Any deviation from tolerance can compromise fit or function and is promptly rejected or reworked. While the body panels are being shaped, another process begins deep inside the battery cell manufacturing area. Tesla, being vertically integrated, produces many of its own lithium-ion battery cells. Raw materials such as nickel, cobalt, manganese, and lithium carbonate are transported into specialized mixing tanks where they undergo slurry formation. These slurries are spread onto copper and aluminum foils, which are then dried in a vacuum oven to form electrodes. Once the electrodes are prepared, they are calendared, flattened to precise thicknesses, and wound or stacked into cylindrical, pouch, or prismatic cells depending on the vehicle model. Each cell is filled with electrolyte solution and hermetically sealed in a dry room to prevent moisture contamination, which could compromise safety or performance. These cells are then loaded into battery modules using robotic pick-and-place arms, which align and connect the terminals with extreme accuracy. The modules are assembled into packs, which include integrated cooling channels, structural support, and electronic control units. These battery packs will eventually be installed into the vehicle's underbody, providing both power and structural rigidity. Back in the body shop, the stamped aluminum panels are robotically welded and riveted together to form the body in white, the term for the car's skeletal shell before any paint or interior components are added. Tesla employs a combination of laser welding, spot welding, and structural adhesive bonding to fuse panels together with minimal distortion and maximum strength. Hundreds of robotic arms suspended from overhead gantries work in synchronized motion, welding, clamping, positioning, all choreographed with software that can adjust in real time based on tolerances and feedback. Laser scanners constantly monitor joint integrity and positional accuracy, ensuring that each weld is correctly formed and precisely located. The body in white at this stage is a gleaming raw aluminum shell, unpainted but fully formed, with all major exterior panels in place, including doors, hoods, and trunk lids, which are often removed and processed separately for better access and quality control. The next destination for the body is the paint shop, one of the most complex and environmentally controlled areas of the entire factory. Before painting can begin, the aluminum body must undergo a chemical pre-treatment process that removes oils, residues, and impurities. This is achieved by submerging the body in a series of baths, alkaline cleaners, deionized water rinses, and ultimately a zirconium or phosphate-based conversion coating that promotes adhesion and corrosion resistance. After drying in an oven to eliminate residual moisture, the body moves into the electrocoating tank, or e-coat stage. Here, the entire shell is submerged in a bath of electrically charged paint particles, which uniformly coat every crevice and interior cavity, ensuring anti-corrosion protection even in areas never visible to the customer. The body is then baked in a curing oven to harden the coating and prepare it for the next layers of paint. The painting process involves multiple coats: primer, base coat, and clear coat. Each coat is applied in sealed spray booths using high-precision atomizing robots, which follow programmed trajectories to ensure even coverage. Advanced electrostatic spray techniques are used to minimize overspray and improve efficiency. After each coat, the vehicle passes through a series of flash and bake ovens to dry and cure the paint, creating the high-gloss finish Tesla vehicles are known for. Once painting is complete, the body heads to the general assembly area, where it begins to transform from an empty shell into a fully operational vehicle. But before any parts are installed, the body undergoes another round of rigorous inspections. Laser alignment systems, gap and flush measuring tools, and robotic probes verify dimensional consistency across every surface. Any discrepancies are flagged and corrected before proceeding. Simultaneously, thousands of components are arriving from various sub-assembly lines and suppliers, including the interior trim, seats, dashboards, glass, wiring harnesses, and powertrain modules. These parts are delivered using automated guided vehicles, AGVs, that navigate the factory floor using embedded magnetic strips or LiDAR-based systems, ensuring just-in-time delivery with minimal human handling. The interior assembly begins with the installation of wiring harnesses, which are laid throughout the vehicle like a nervous system. These harnesses, containing kilometers of wire, are clipped into designated paths along the floor, pillars, and roof. Robots and human technicians work together, ensuring connectors are correctly routed and terminals are securely fastened. Next, the HVAC components, dashboard structure, and infotainment systems are installed, followed by airbags, sound insulation, and seat frames. At each step, torque-controlled tools and digital confirmation systems ensure that every fastener meets the required specification. The vehicle's panoramic glass roof, a signature element of Tesla's design language, is then lowered into place using vacuum suction lifters and laser-guided alignment tools. A two-part adhesive is applied by robotic nozzles to create a watertight seal. The doors, previously processed separately, are reattached and calibrated to ensure perfect alignment and smooth operation. Tesla's frameless door design and automatic opening features require particularly tight tolerances and sensor calibration. With the interior taking shape, the vehicle proceeds to powertrain integration, where the battery pack, assembled and tested in a parallel process, is lifted by robotic jigs and bolted into the vehicle's underbody using a sequence of torque-controlled actuators. The drive units, whether dual or tri-motor, are then installed onto the front and rear subframes, connected via suspension arms and motor mounts that are pre-aligned using precision fixtures. With the battery pack securely mounted and the drive units in position, the vehicle is now ready to undergo one of the most critical transitions in the entire manufacturing process: electrical and software activation. While the car may appear nearly complete, it is still lifeless. No lights, no screen activity, no sensor communication. This stage, often referred to as initialization, is where the vehicle essentially takes its first breath. A technician connects a diagnostic interface to the vehicle's central computer, usually via a secure data port under the dash, and uploads the foundational firmware that activates the vehicle's electronic control units, or ECUs. Each Tesla contains dozens of ECUs distributed throughout the chassis, responsible for everything from motor control to autopilot systems, battery thermal regulation, infotainment, and safety monitoring. Tesla's approach to software architecture is notably centralized compared to traditional automakers. Instead of relying on fragmented systems developed by various suppliers, Tesla has developed an in-house software stack that enables over-the-air updates, real-time diagnostics, and direct integration between mechanical systems and the vehicle's neural net. Once the firmware is loaded, a cascade of subsystems begins to power on. The touchscreen illuminates for the first time. The instrument cluster boots up. Cameras begin streaming to internal diagnostics. Every sensor, switch, and relay goes through a self-check process that verifies communication with the vehicle's central gateway. Any issues, such as a disconnected wire, a miscalibrated radar unit, or a sensor failure, are immediately logged for remediation. At this stage, even something as minor as a single LED malfunction will halt the progression until it's resolved. Next, attention turns to calibrating the advanced driver assistance systems. Tesla's autopilot suite relies heavily on an array of forward, rear, and side-facing cameras, ultrasonic sensors, and radar or LiDAR, depending on the model and hardware iteration. These units must be precisely aligned within the bodywork to ensure accurate environmental perception. Calibration is not just mechanical, but also algorithmic. As the vehicle is rolled into a controlled calibration zone, a series of reference panels, patterns, and 3D markers are placed around the car. Cameras are activated, and software compares live imaging data against known coordinates to fine-tune the visual input. The system will not pass if even a single camera is slightly skewed or obstructed. Following this, the wheels and tires are mounted, another process where automation and precision intersect. Each wheel assembly, comprising the tire, alloy rim, TPMS sensor, and balancing weights, is prepared in an adjacent sub-assembly cell. Robotic arms select the correct wheel variant depending on trim level and mount it onto the vehicle's wheel hub using torque-monitored tools. Once installed, the wheels are not yet fully ready for the road. They must be aligned. Wheel alignment takes place on a dedicated platform, where laser or camera-based alignment tools measure caster, camber, and toe angles in real time. Adjustments are made on the spot using robotic wrenches that turn suspension bolts until readings fall within micrometer level tolerances. Proper alignment is vital not only for performance and safety, but also for autopilot accuracy, as steering bias or drift could interfere with the vehicle's self-driving capabilities. Now we arrive at one of the most impressive parts of Tesla's assembly process: final assembly verification and end-of-line testing. This begins with a full-body water intrusion test. The completed vehicle is driven, or in some cases, automatically transported, into a sealed chamber known as the water test booth. High-pressure nozzles blast the car from all directions, simulating rain, puddle splashes, and pressure washing. Sensors inside the cabin monitor for even the slightest moisture intrusion. Any leak, even a trace around the door seals or underbody joints, results in a stop and targeted repair. Once the vehicle passes the water test, it moves into dynamic testing. But before that can begin, it must first pass a rolling road diagnostic check. The vehicle is positioned on a set of rollers that simulate driving conditions. Here, Tesla technicians run through a wide range of operational checks. Motor response is tested across a variety of simulated terrain profiles. Regenerative braking systems are evaluated to confirm energy recovery rates match expected values. HVAC systems are activated to check for proper airflow, temperature regulation, and acoustic performance. Inside the cabin, the touchscreen interface undergoes a systems integrity test. Each menu, function, and button is activated in sequence. The infotainment system is tested for connectivity to Tesla's software servers. Navigation modules are initialized. Bluetooth and Wi-Fi antennas are pinged. Microphones and speakers are checked for distortion or static. The cabin camera, located near the rearview mirror, is tested for focus and response to light changes. The glove box, front latch, trunk motors, and window regulators are also checked for proper operation and speed. After static diagnostics, the vehicle is finally ready for its low-speed dynamic test. On-site test tracks, usually located adjacent to or within the Gigafactory premises, allow each vehicle to undergo a short but comprehensive road test. The driver is usually a trained Tesla technician who runs the car through a prescribed routine: acceleration from 0 to moderate speeds, emergency braking, tight cornering, and high-speed lane changes. This test evaluates suspension response, noise levels, steering feel, and drivetrain behavior under real load conditions. The vehicle's software continues to log performance data throughout the drive, flagging any anomalies. After returning from the test track, the car enters the final visual inspection area. Here, a team of human inspectors, armed with light panels, bore scopes, and digital checklists, reviews every visible surface inside and out. Paint quality is scrutinized for orange peel texture, swirl marks, or dust nibs. Panel gaps are measured by hand and with laser gauges. The interior is inspected for material alignment, stitching accuracy, and uniform texture. Every single button, vent, trim piece, and fixture is physically touched and verified. If the vehicle passes this multi-layered gauntlet of inspections, it moves into what's known as pack out, the final preparation area before shipment. Here, the car receives its VIN label, ownership documentation, and destination configuration. This is where region-specific software settings, navigation maps, and language preferences are loaded. The final battery charge is administered, usually to around 90%, before the vehicle is powered down and prepared for transport. Each Tesla is now ready to leave the factory, but even this step is a study in logistical precision. Automated systems coordinate the movement of completed vehicles from the final inspection bay to outbound logistics. Depending on destination, the vehicle may be loaded onto a covered rail car, placed into a secure car carrier, or transferred to a nearby delivery hub. RFID tags embedded in the vehicle identify it to tracking systems that monitor its journey to the customer. It is important to note that Tesla's manufacturing ethos is grounded in continuous improvement. Unlike traditional automakers that rely on annual model cycles, Tesla frequently changes its assembly lines in real time, updating hardware or processes based on production learnings, user feedback, and software improvements. This philosophy means that even within the same week, two identical models may have subtle differences in componentry, firmware version, or assembly methods. These continuous upgrades are made possible by Tesla's heavy reliance on vertical integration and factory-level data analytics. Every torque wrench, sensor, robot, and diagnostic station feeds data into a centralized factory control system. Engineers analyze this data daily, making adjustments to improve efficiency, reduce rework rates, and enhance vehicle quality. This feedback loop between digital twin modeling, live production, and field performance is one of the reasons Tesla has been able to scale quickly while maintaining product innovation. With the vehicle now fully assembled, inspected, and approved, it embarks on the final leg of its journey: delivery to the customer. Whether arriving at a showroom, a regional distribution center, or directly to a driveway via Tesla's direct delivery program, the finished product represents not just a vehicle, but the culmination of thousands of interconnected systems working in harmony, each with millisecond-level precision, each tuned for performance, safety, and the future of mobility. Once a Tesla vehicle has cleared its final inspection and receives its shipment authorization, the journey from the Gigafactory to the customer begins. Unlike conventional auto manufacturers, which often rely on third-party dealership networks and extensive warehousing chains, Tesla's direct-to-consumer delivery model has radically simplified and streamlined this phase. Yet, behind that apparent simplicity lies a highly coordinated logistical infrastructure, optimized to handle the massive volume of vehicles produced daily across multiple global factories. At this stage, the vehicle is routed into a specialized outbound logistics yard, a designated section of the Gigafactory site, or an adjoining facility engineered specifically for the staging, sequencing, and transportation of finished vehicles. Each car is tagged with a digital shipping label that contains its vehicle identification number, model variant, color, wheel configuration, destination, and special instructions such as left-hand versus right-hand drive. This digital manifest is cross-referenced with Tesla's centralized logistics control software, ensuring that each car is placed into the correct regional batch for dispatch. Automated tug vehicles, similar to those used in airport ground operations, tow trailers of Tesla vehicles into position. If the vehicle is destined for domestic delivery, it is typically loaded onto a car carrier truck designed to hold 7 to 10 units. These carriers are scheduled to depart in tightly timed intervals, with software routing each truck for the most efficient delivery path based on real-time traffic, weather, and destination inventory levels. For international shipments, the process shifts slightly. Vehicles bound for overseas markets are loaded onto rail cars or container haulers that transport them to port facilities. At the port, the vehicles are driven onto roll-on/roll-off ships, a type of cargo vessel with built-in ramps and internal decks specifically designed for transporting cars. Each Tesla is parked and secured inside the vessel, often alongside other vehicles of the same batch, in a configuration that minimizes offloading time upon arrival. Throughout this journey, every vehicle remains digitally visible to Tesla's logistics team. GPS tags, onboard cellular connectivity, and carrier integration systems allow real-time tracking from the moment the vehicle leaves the plant to the moment it is delivered to the end customer. This level of transparency enables Tesla to forecast delivery windows with a high degree of accuracy and proactively resolve issues like weather delays or customs bottlenecks. Meanwhile, Tesla's delivery centers and service hubs are preparing to receive the vehicles. These locations, often converted warehouse spaces or minimalist showrooms, act as regional fulfillment points. Upon arrival, each vehicle undergoes a final pre-delivery inspection. This includes checking tire pressures, topping off windshield washer fluid, confirming that the software version is current, and ensuring the paint and interior remain in pristine condition. The protective coverings applied during shipment, such as plastic seat covers and foam door guards, are removed, and the car is detailed for presentation. If a customer has opted for Tesla's home delivery option, the vehicle may be dispatched from the delivery center directly to the buyer's driveway using either a flatbed or a mobile technician. Tesla's minimalist approach to delivery day often involves minimal paperwork, since much of the ownership transfer process is handled digitally ahead of time. Customers sign final documents electronically, receive a tutorial on using their new vehicle via the in-car interface or mobile app, and are given access to Tesla's expansive digital support ecosystem. But delivery is not the end of the story. It's merely the handoff point between manufacturing and long-term ownership. Tesla's commitment to post-production support is tightly integrated into its digital platform. The same software and hardware systems that facilitated the car's birth on the factory floor now serve as tools for its ongoing evolution. Over-the-air updates are one of the most defining characteristics of the Tesla ownership experience, and they depend on a robust ecosystem of remote diagnostics, data collection, and machine learning feedback loops. Every Tesla on the road constantly reports anonymized performance data back to Tesla's servers. This includes battery health, motor efficiency, navigation anomalies, autopilot behavior, sensor readings, and even software bugs. Engineers at Tesla's headquarters use this data to refine algorithms, push updates to correct inefficiencies, and enhance safety features, all without the owner needing to visit a service center. This dynamic software lifecycle, enabled by the tightly coupled manufacturing and software teams, makes Tesla vehicles unique in their ability to improve long after leaving the factory. Meanwhile, Tesla's service infrastructure continues to grow alongside its production volume. Instead of relying entirely on traditional service centers, Tesla employs a mobile service strategy wherever possible. These service vans are equipped with diagnostic tools, replacement parts, and certified technicians who can perform a wide range of repairs or updates at the customer's location. The ability to diagnose and even preemptively fix issues before they affect the driver is rooted in the precision and data fidelity achieved during the original manufacturing process. Looking back toward the factory, it's important to understand how Tesla's architectural philosophy supports this entire life cycle. Every gigafactory is designed not just to build vehicles, but to serve as a data hub, a testing ground, and a self-improving machine. These plants are built with flexibility in mind, using modular assembly lines that can be reconfigured on the fly. Instead of fixed conveyor belts, Tesla often uses autonomous mobile robots and smart material flow systems that can reroute components or vehicles as production needs change. The Gigafactory floor is not one continuous line, but a series of interconnected stations. Each one is equipped with sensors, machine vision, and feedback modules that report into a central factory operating system. This system not only tracks current production metrics, but also simulates process optimizations. For example, if a torque reading at a robotic arm consistently falls within the low-end threshold, engineers can be alerted and update the robot's behavior before a quality deviation even occurs. This predictive control approach reduces downtime and increases first-pass yield, meaning more vehicles pass inspection on the first try without needing rework. Vertical integration plays a critical role in making this system work. Tesla doesn't just assemble parts, it manufactures many of them. From battery cells to electric motors, from infotainment chips to firmware code, Tesla has brought traditionally outsourced operations in-house. This reduces dependency on suppliers, shortens feedback loops, and allows the company to innovate rapidly. For instance, if a new battery chemistry is developed in Tesla's R&D lab, pilot-scale production can begin almost immediately within a section of the existing Gigafactory, without the need for third-party approval or infrastructure overhaul. Even Tesla's supply chain reflects this philosophy of speed, control, and adaptability. Critical materials like lithium, nickel, and cobalt are sourced through long-term contracts with mining operations. And in some cases, Tesla has invested directly in extraction or refinement operations. These materials are routed directly to gigafactories or regional production hubs, bypassing many of the bottlenecks that affect traditional automakers who rely on complex supplier tiers and international freight forwarding. This system is further enhanced by Tesla's real-time digital twin architecture. a virtual replica of the entire manufacturing process. Every machine, part, and process is mirrored in a digital environment that can simulate disruptions, forecast efficiency gains, and run hypothetical scenarios. Want to test how a new weld technique might affect throughput? The digital twin can simulate that change in minutes, allowing engineers to make data-backed decisions that translate directly into physical adjustments. Through all of these layers, physical infrastructure, software integration, vertical manufacturing, and delivery logistics, Tesla has redefined what modern automotive production looks like. It's not just about building cars, it's about building a system that builds itself smarter with every iteration. Every vehicle produced feeds data back into this system. Every manufacturing anomaly becomes a learning opportunity. Every software update enhances not just the product, but the factory's ability to produce the next one even better. What this means is that the Gigafactory isn't a static building. It's a living organism, a self-correcting, self-improving entity designed not only to produce cars, but to redefine what a car even is in the age of autonomy, electrification, and artificial intelligence. And at the center of this vision lies a carefully choreographed dance of machinery, people, data, and innovation, all working in harmony to create not just a vehicle, but a new standard for the global auto industry. Inside a Tesla Gigafactory, perhaps the most mesmerizing and defining visual is the near-symphonic choreography of robots working in harmony. Tesla employs tens of thousands of industrial robots across its global facilities, many sourced from automation giants like KUKA and FANUC, and many others developed in-house. But these aren't the slow, single-arm welders of traditional auto plants. These are high-speed, multi-axis machines operating in tightly coordinated clusters that resemble mechanical dance troupes, fast, precise, and relentlessly efficient. The bulk of these robots are deployed in the body shop, where raw stamped panels are joined to form the body in white. Here, multiple robot arms work within inches of one another, one positioning a panel, another applying structural adhesive, and a third completing a weld, without ever colliding. This level of spatial awareness is made possible by a digital supervisory system that orchestrates each motion path in microseconds. Each robot is fitted with a suite of sensors, including force feedback, proximity detectors, and sometimes even cameras, allowing them to adapt slightly if a panel is marginally misaligned or a weld point needs micro adjustment. In many production cells, Tesla has implemented what are known as friction stir welding units, robots capable of joining aluminum panels without melting them. This technique, originally developed for aerospace manufacturing, uses a high-speed rotating tool that generates frictional heat to soften and fuse materials without introducing impurities or thermal distortion. It results in stronger joints and is especially effective for joining thick battery pack casings or high-stress structural nodes. But Tesla's automation does not end at the mechanical level. Surrounding the physical robots is a vast digital control infrastructure powered by machine learning algorithms that analyze every torque value, weld voltage, and robot movement. These systems compare every single action against historical data to identify patterns that may indicate future faults. For example, if a particular welding arm shows a slight uptick in motion latency or current draw, the system can schedule predictive maintenance before a full failure occurs. This predictive maintenance loop dramatically increases uptime and reduces unexpected halts in the production line. Complementing this robotic workforce is a carefully integrated human team. Contrary to the misconception that gigafactories are purely robotic, Tesla maintains a robust human workforce in areas where judgment, dexterity, or problem solving are still superior to automation. For instance, interior trim installation, particularly tasks involving soft materials like Alcantara, stitched leather, or delicate wiring, still relies on trained technicians who can feel for correct tension, align materials by eye, and make subtle corrections during fitment. Human workers are also essential during final inspection, dynamic testing, and exception handling. If a part doesn't meet specifications, or if a software glitch prevents a subsystem from booting, it's often a human specialist who diagnoses and resolves the issue. These employees are equipped with digital tablets linked to Tesla's internal manufacturing cloud. They receive live data feeds from the vehicle's onboard sensors and can pull up schematics, tolerances, and previous production history in seconds. Every fix they apply, every note they enter, becomes part of that car's digital footprint, a log that follows it forever, even into post-sale diagnostics. Tesla's approach to worker efficiency is also shaped by ergonomic engineering and cognitive load optimization. Workstations are designed to reduce repetitive strain injuries with tool arms that balance heavy equipment and lift assists for placing components. Augmented reality overlays are sometimes used during training phases, projecting digital guides onto surfaces to help new employees understand complex assemblies. Rotational schedules ensure workers shift between physically demanding tasks and more routine duties, helping prevent fatigue-related errors. As we dig deeper into the brain of the Gigafactory, we arrive at what is perhaps Tesla's greatest long-term differentiator: the use of artificial intelligence, not just in the vehicles, but within the factory itself. Tesla doesn't merely automate individual machines, it trains its factories to optimize themselves. This is achieved through a combination of real-time data ingestion, cloud-based analytics, and reinforcement learning loops. Let's take an example from the paint shop. Traditionally, robots follow predefined spray paths based on CAD data. However, Tesla trains its painting robots using vision-based systems that analyze each body shell in real time for curvature, panel orientation, and gap uniformity. This data informs dynamic adjustments to spray trajectory, nozzle pressure, and stroke timing. The result is more uniform coating, fewer touch-ups, and improved long-term finish durability. Or consider battery pack assembly. Each cell inserted into a module is monitored for voltage, internal resistance, and capacitance. Tesla uses this data to build a profile of every module's thermal characteristics. If a pattern of abnormal cell degradation is observed in the field, engineers can trace it back to the exact production batch, process variables, or even environmental conditions at the time of assembly. This data loop enables retroactive improvements to manufacturing conditions and helps refine pack longevity models for future software updates. One of the more futuristic systems Tesla is rolling out across its newer Gigafactories involves swarm intelligence for material transport. Rather than fixed conveyor systems, Tesla uses fleets of autonomous mobile robots that navigate the factory floor using SLAM algorithms. These robots aren't programmed with fixed paths. They learn optimal routes in real time, adapt to obstacles, and communicate with one another to avoid collisions or bottlenecks. This approach allows the factory layout to be more modular and reconfigurable, supporting agile production and faster adaptation to new models or variants. Equally fascinating is Tesla's use of simulation environments for factory operations. Entire sections of the Gigafactory are mirrored in a digital twin, an exact 3D replica of the physical space and its processes. Engineers can run simulations to test new workflows, evaluate machinery upgrades, or even plan how to integrate a new vehicle platform without ever disrupting the live production line. If a simulated robot collision is detected, the system can suggest path modifications or sequence changes before real-world implementation. This same philosophy extends to Tesla's use of custom silicon chips. While best known for its full self-driving computer, Tesla also designs specialized hardware for internal factory use. These include image recognition chips optimized for high-speed defect detection, edge computing units for data processing at the machine level, and embedded control systems that allow more precise energy regulation in welding and curing ovens. This level of hardware customization provides Tesla with granular control over quality, energy efficiency, and process speed. Another compelling layer of Tesla's factory evolution involves environmental engineering. Every gigafactory is designed with sustainability as a core tenet. Rooftop solar arrays, on-site water recycling systems, and battery-powered internal logistics vehicles are just some of the components contributing to closed-loop manufacturing. The energy used to produce each Tesla vehicle is increasingly being sourced from renewable systems within the facility itself, dramatically lowering life-cycle carbon emissions. Tesla's focus on vertical integration again becomes critical here. When energy systems, battery chemistry, robotics, and software all originate from the same corporate ecosystem, coordination becomes exponentially easier. Design tweaks to the battery casing, for example, can immediately inform changes to the casting molds, welding fixtures, or software-based thermal models, without the friction of cross-company coordination. Perhaps the most emblematic symbol of this holistic integration is Tesla's gigacasting machines. These are among the most powerful aluminum die casting machines in the world, capable of creating entire underbody sections as a single solid piece. These machines, designed in partnership with H2R, reduce the number of parts in the vehicle's chassis from hundreds to just a few, eliminating fasteners, reducing weight, and improving crash performance. Integrating such massive components into the production line requires not just physical reconfiguration, but software integration, supply chain alignment, and real-time QC adaptation, all of which Tesla is uniquely positioned to manage in-house. As we look at the sum of all these systems, robotics, AI, digital twins, human-machine interfaces, gigacasting, and energy-conscious infrastructure, it becomes clear that the Tesla production process is not simply a variation on traditional automotive manufacturing. It is an entirely new operating system for building cars. A platform, not just a plant. A fusion of machine intelligence, predictive analytics, physical innovation, and agile design thinking, all operating under a single cohesive philosophy. The Tesla Gigafactory isn't just where vehicles are built. It's where ideas are born, tested, scaled, and refined in real time. Where the boundary between hardware and software dissolves. Where every sensor, every weld, and every decision feeds back into a growing repository of knowledge that powers the next generation of vehicles, robots, factories, and systems. One of the most disruptive engineering breakthroughs in Tesla's modern manufacturing playbook is the integration of the structural battery pack, a complete rethinking of how the battery, chassis, and underbody of the vehicle work together. In traditional automotive design, the battery pack is a standalone component, an energy container bolted to the car's underbody. But in Tesla's structural pack architecture, pioneered with the 4680 battery format, the battery no longer rides beneath the structure, it becomes the structure. To understand the scale of this shift, we first need to explore the 4680 cell itself. Named for its dimensions, 46mm wide and 80mm tall, the 4680 cylindrical lithium-ion cell represents a significant departure from the older 2170 and 18650 formats. It offers 5 times the energy, 6 times the power, and reduces the cost per kilowatt hour significantly. But it's not just the size that matters, it's how the cells are built and what they enable downstream in manufacturing. Each 4680 cell is designed to support tabless internal architecture. In conventional cells, current must travel through a tab, a narrow conductor that can create resistance and heat. In Tesla's tabless design, the entire edge of the rolled electrode acts as a current collector, enabling more uniform heat distribution and higher current throughput. This drastically reduces internal resistance, improves efficiency during charge and discharge, and simplifies thermal management, a critical benefit when assembling high-density battery modules. These cells are produced in a vertically integrated line that starts with electrode slurry mixing, followed by coating, calendaring, cutting, and winding, all performed under strict environmental control. The wound jelly rolls are inserted into steel canisters, filled with electrolyte, sealed by laser welding, and then aged, tested, and sorted. What's remarkable is that Tesla's battery lines are not just production machines, they are learning machines. Each stage of battery cell production is heavily instrumented, with sensors that track viscosity, coating uniformity, line tension, and thermal behavior. These metrics feed back into AI-driven quality control systems that adapt in real time, reducing scrap rates and improving yield without requiring line shutdowns. Once the cells are complete, they are no longer assembled into modules as in traditional EVs. Instead, Tesla places them directly into the structural battery pack housing, eliminating intermediary module structures. This pack is a part of the vehicle's load-bearing frame, not an add-on. The cells are bonded in place using structural epoxy, and this bonded matrix provides rigidity akin to an aircraft's wing box design, a technique borrowed from aerospace engineering. A critical enabler of this approach is the use of high-performance structural foams and thermal adhesives. These materials serve multiple functions simultaneously. They manage vibration and noise, conduct heat away from the cells to integrated cooling loops, and crucially, form part of the vehicle's crash energy management system. During side or front impacts, the structural battery pack helps distribute forces across a wider area, reducing localized deformation and improving occupant safety. In the Gigafactory, structural pack assembly is a distinct line, physically separate from standard battery operations due to its unique tooling requirements. Cells are loaded into the pack casing using high-speed robotic insertion machines. Adhesive dispensing systems apply precisely metered quantities of two-part epoxy at high pressure. Once cells are in place, the entire structure is cured in massive industrial ovens that bring the adhesive to full mechanical strength. After cooling, the pack undergoes precision machining to create interfaces for the drive unit, seat mounts, and body attachment points. What results is not just a battery, it's a central element of the vehicle's physical frame. The top of the pack often serves as the interior floor of the cabin. The bottom, reinforced by ribbed aluminum or composite materials, acts as the underbody and aerodynamic tray. By combining energy storage, structural support, and crash safety into a single unit, Tesla eliminates dozens of separate components, reducing mass, simplifying manufacturing, and slashing costs. Now, integrate this with another innovation, gigacasting. Tesla's use of giant aluminum die casting machines to form the front and rear underbody sections of its vehicles is nothing short of revolutionary. These Idura Giga Press machines, weighing over 400 tons and applying clamping forces in the range of 6,000 to 9,000 tons, can create entire frame sections as a single cast. Instead of welding together hundreds of stamped components, Tesla now forms massive structural elements in one shot, lighter, stiffer, and far faster to produce. When the front and rear castings are combined with the central structural battery pack, Tesla essentially builds the entire underbody of a vehicle using just 3 large parts. These unibody trios replace what was once over 300 parts in older chassis architectures. This not only reduces complexity and assembly time, but also minimizes the number of suppliers, welds, fixtures, and potential quality defects. Each casting is inspected via X-ray and ultrasonic imaging to detect porosity, cracks, or incomplete fills. Any anomalies are rejected and remelted, maintaining a closed-loop aluminum recycling system. This radical simplification also redefines how the rest of the car is built. Traditional automotive factories are organized around a highly linear body-in-white process: frame construction, then floor pan, then underbody integration. Tesla's method is more like assembling a modular aircraft, where large subassemblies are brought together at fewer, more tightly controlled junctions. This allows Tesla to create more compact factories with faster cycle times and fewer workers per unit produced, metrics that directly impact capital efficiency and return on investment. To support these next-generation designs, Tesla continues to invest heavily in materials science research, much of it focused on high-strength aluminum alloys, advanced polymers, and die-casting feedstock refinement. The development of proprietary aluminum alloys that combine excellent flow characteristics in casting with high tensile strength post-treatment is a crucial part of making gigacasting work. These alloys must cool evenly, avoid brittleness, and withstand both crash loads and environmental exposure over time. In parallel, Tesla is exploring dry electrode manufacturing for future battery lines, a technique that eliminates the solvent-heavy coating and drying stages currently used in electrode production. Dry electrodes can be applied directly to the current collector using pressure and heat, significantly reducing energy consumption, production footprint, and cost. This aligns with Tesla's vision for more sustainable, vertically integrated gigafactories, ones that consume fewer resources per gigawatt hour and can be rapidly scaled in new geographies. Indeed, Tesla's goal is not just to build more cars, it's to scale manufacturing like a technology company, not an industrial one. This means shorter ramp-up times, smaller capital expenditures per unit of output, and a globally unified software-hardware stack that can be deployed anywhere in the world with minimal localization. Future gigafactories, like those planned in Mexico and India, are being designed with these structural pack and casting concepts at their core, meaning they won't just produce the next generation of Tesla vehicles, they will be born already optimized for speed, simplicity, and flexibility. This systems thinking extends even further into factory floor layout and material flow logistics. With fewer total parts, Tesla can implement straighter, more continuous material pathways, reducing the need for kitting, buffering, and material staging. Instead of having dozens of sub-assembly lines feeding hundreds of components, Tesla can deliver entire modules, like castings or packs, straight to the marriage station, where the vehicle begins to take its final form. This layout change reduces floor space, lowers error rates, and improves throughput. It also allows for greater software simulation of factory dynamics. When each vehicle only passes through 30 or 40 production cells, rather than 200 or 300, it becomes computationally feasible to simulate the entire factory in real time. AI-based systems can then test flow changes, balance labor loads, and reroute production if a bottleneck emerges, all before any change is implemented on the floor. The result is a self-learning, self-optimizing factory capable of adapting to demand shifts, supplier disruptions, or design updates faster than legacy automakers can retool a single line. All of this innovation, structural batteries, 4,680 cells, gigacasting, and software-first factories converges into a clear strategic objective: build more cars, better and faster, with fewer people and lower capital costs per unit. It's not about squeezing the last drop of efficiency from legacy systems. It's about replacing those systems entirely. And the boldness of that approach is why Tesla's manufacturing story remains one of the most closely watched industrial transformations of the 21st century. Our journey begins deep within the steel supply and stamping operations, far from the glittering finish lines of final inspection. The G-Class starts life as a collection of raw, flat metal panels. These panels, primarily high-strength steel, are delivered to the facility in massive coils, which are unrolled and leveled before being fed into industrial press machines. These presses apply thousands of tons of pressure to shape the steel into the various foundational parts of the G-Class body, such as the floor pan, door skins, roof frame, and iconic flat body panels. The unibody shell is not used in the G-Class. Instead, it's built with a ladder frame chassis, a method more common in heavy-duty trucks. This makes the process both more rugged and more complex, requiring each piece to be perfectly formed to exact tolerances. Once the panels are pressed, laser-guided robotic arms trim and smooth the edges with astonishing precision. Each cut is planned digitally down to the 1/10 of a millimeter, ensuring uniformity across thousands of units. Now we move into the body-in-white phase, the initial stage of structural assembly. Here, the stamped panels are arranged into sub-assemblies. The floor pan, side frames, firewall, and roof supports are meticulously aligned on a series of jig fixtures. These large, articulated steel mounts hold each piece in perfect position for welding. But unlike many modern car factories where robot arms zip through spot welds in a blur, the G-Class body is largely welded by hand. Dozens of skilled technicians, each highly trained, wield welding torches in a choreographed dance of sparks and heat. More than 6,000 welds are performed on each body, reinforcing the vehicle's structural rigidity. As they go, workers constantly inspect joints visually and mechanically using go-no-go gauges to confirm tight fits and ensure that structural integrity is never compromised. The welding process is a symphony of patience and expertise. Welders must account for heat distortion, managing the order and location of each weld to maintain the geometric accuracy of the body. They use pneumatic clamps, steel rulers, and laser levels to ensure that the angles and lines of the body remain true. It is here that the G-Class's signature upright posture begins to take shape. Those vertical window frames, slab-sided doors, and angular corners that give the vehicle its commanding silhouette. They're all defined and locked into place during this early phase. Once the body is fully welded and structurally complete, it undergoes a process known as metal finishing. This is where skilled craftsmen examine every seam, edge, and panel for imperfections. Small hammers, abrasives, and filler tools are used to smooth out inconsistencies. The goal is to achieve a surface that will accept paint without a single visible ripple or deformity. The attention to detail here is extraordinary. What may seem like an invisible bump to the naked eye will be caught later by paint defects if not resolved. Technicians in this stage often use high-powered overhead lights and fingertip inspection techniques to feel for irregularities. And yes, they still do it by touch. Technology can detect misalignments, but it's the trained human hand that often finds the smallest flaws. Once the body in white has passed inspection, it is ready for paint preparation. But before any color is applied, the shell undergoes a rigorous cleaning process. It is first immersed in a series of chemical baths, alkaline cleaners, degreasers, and deionized water rinses that strip away all traces of oils, residues, or contaminants from the welding and finishing stages. Then it moves into the e-coating process. This is where the body shell is dipped into a giant electrocoating tank filled with anti-corrosion primer. An electrical current is applied, causing the primer to bond to the metal surface at a molecular level. Every nook, crevice, and corner is coated evenly, providing unmatched rust protection. The G-Class was originally built for military duty, and this durability-focused philosophy continues today. After the e-coating, the body is cured in an oven at temperatures around 180 degrees Celsius. The curing hardens the primer and sets the foundation for the paintwork that will follow. Then comes the application of the base coat, color layers, and clear coat, each sprayed meticulously in high-tech painting booths. The factory offers a broad range of colors, from conservative blacks and silvers to vibrant custom finishes from the G Manufacturer Personalization Program. Incredibly, many G-Class vehicles receive their paint by hand spraying, not automated robots. This allows greater control and customization for two-tone finishes, matte effects, and hand-masked accents. The painted body then returns to another round of inspections. Factory workers use light tunnels and soft cloths to detect even the smallest specks of dust, paint sagging, or orange peel textures. If needed, technicians wet sand and polish the affected areas manually. This is one of the most time-consuming parts of the process, but it ensures that the G-Class leaves the paint shop with a flawless, mirror-like surface. With the body now painted and prepped, attention turns to the chassis, the rugged ladder frame that defines the G-Class's off-road DNA. Unlike unibody cars, where the structure and body are fused, the G-Class separates these two elements, a design that offers superior strength and modularity. The chassis is fabricated from thick-gauge steel and welded into a rectangular framework with multiple crossmembers and mounting points. It's engineered to endure extreme torsional loads from uneven terrain, rock crawling, and high-speed travel over unpaved surfaces. The entire chassis is then treated with a special powder coating that protects it from gravel, salt, moisture, and mechanical wear. At this point, the chassis begins its mechanical assembly. Giant overhead conveyors lift it into place on a moving assembly line. Suspension components are added first. The G-Class uses a double wishbone front suspension and a rigid rear axle with trailing arms and coil springs, all designed for articulation and ride comfort. Workers mount control arms, install air or coil springs depending on the configuration, and torque each fastener to precise specs using digital torque wrenches that record every application for quality traceability. Drive shafts, differentials, and the transfer case follow next. The G-Class features 3 locking differentials, front, center, and rear, making it one of the most capable factory off-roaders ever built. These components are pre-assembled in sublines and arrive at the main chassis line just in time for installation. Each differential is bench tested before being mounted, and once installed, hydraulic and electronic connections are secured and checked for sealing integrity. Next, the engine and transmission arrive. These powertrains are built separately, typically at Mercedes powertrain facilities, and delivered fully dressed with wiring harnesses, fuel systems, and control modules already in place. A robotic hoist lowers the engine and transmission into the chassis as technicians bolt it down to reinforced subframe mounts. The transmission tunnel is lined with heat shielding and the exhaust system is connected. Stainless steel manifolds, catalytic converters, and mufflers are all aligned with laser guidance systems to ensure proper clearance and vibration isolation. As the powertrain is secured, attention turns to the braking and steering systems. High-performance disc brakes with multi-piston calipers are installed on each wheel hub. Brake lines are routed with stainless steel fittings and then bled using automated vacuum machines to ensure a perfect seal and no air bubbles. The power steering rack is attached and aligned, and its fluid circuits are pre-flushed to remove any contaminants. At this stage, the chassis is essentially a rolling platform, ready to meet the painted body that has been traveling in parallel on a separate line. Continuing our journey into the heart of the Mercedes-Benz G-Class assembly process, we arrive at the moment of mechanical matrimony, a pivotal point known within the factory as the marriage. This step is one of the most anticipated stages in any automotive plant, but here in Graz, it carries almost ceremonial weight. The moment when the meticulously painted body is lowered onto the fully built ladder frame chassis transforms a collection of high-grade parts into what begins to truly resemble a finished G-Class. The process begins with both the body and the chassis arriving at the marriage station on 2 separate automated conveyor lines. Precision and timing are essential. As the chassis is lined up beneath the suspended body shell, a series of hydraulic lifts and alignment pins begin the delicate work of bringing the two together. Technicians verify multiple reference points using laser measurement tools to ensure the body mounts align perfectly with the corresponding points on the chassis. The process may appear straightforward, but in reality, the tolerances are extremely tight, within a single millimeter. Any deviation could lead to misaligned panels, noisy interiors, or handling inconsistencies. Once the alignment is verified, the body is carefully lowered using a multi-axis robotic gantry system. Specialized bushings are inserted between body and frame to absorb vibrations, and bolts are torqued down using synchronized electric torque tools. These tools not only apply the correct force, but also record each torque event digitally for traceability. In total, dozens of mounting points are secured during this stage, creating a permanent bond between body and chassis. With the vehicle now structurally complete, the next steps shift focus to the installation of electrical systems and interior components. The G-Class is known for its advanced technology, luxury appointments, and off-road capability, all of which require an intricate network of electronics. Wiring harnesses are delivered to the line pre-assembled and bundled according to specific vehicle configurations. Each harness includes connectors for power distribution, lighting, infotainment, sensors, airbags, and the drivetrain management system. Installation of these harnesses is done mostly by hand due to the complexity and variability of options in each vehicle. Workers snake thick bundles of cables through the body structure, routing them through the firewall, behind the dashboard frame, under the floor, and along the roof rails. Clamps and cable guides ensure the wiring remains secure and doesn't rattle or chafe over time. Diagnostic computers are connected at this stage to confirm continuity, check for shorts, and verify module communications over the vehicle's CAN bus network. While this is happening, the HVAC system is assembled and installed. This includes the heater core, evaporator unit, blower fans, and electronic control motors that adjust airflow and temperature zones. The G-Class features multi-zone climate control, so ducting is routed with exacting precision through the dash, footwells, and rear cabin areas. Once the climate system is in place, the dashboard sub-assembly is installed as a single module. This enormous component includes the infotainment screen, control buttons, ambient lighting strips, and the central air vents. Workers use vacuum suction lifts to guide the dash into place without damaging the painted surfaces or soft leather trim. Now comes one of the most craftsmanship-intensive stages in the entire production, the installation of the interior. Unlike many mass-produced vehicles that use synthetic fabrics and machine-mounted panels, the G-Class is fitted largely by hand, using real materials: leather, wood, aluminum, and piano black lacquered plastics. The seats are built separately and upholstered using hides that are individually inspected for imperfections. Skilled trimmers sew the leather together, using double stitching patterns that match the exterior color or the customer's specification. Once finished, the seats are bolted into the vehicle with electronic seat module calibration to ensure proper memory function and lumbar support. Door panels follow next. These are assembled in parallel stations where components like speaker grills, switches, ambient lighting, and leather inserts are bonded together before being mounted. Each panel is carefully pressed into place and tested for fit, sound insulation, and tactile feedback. The sound of a G-Class door closing is legendary, an unmistakable mechanical clunk that speaks to solidity. Achieving this sound requires a precise interplay of hinges, rubber seals, door weight, and locking mechanism geometry. Carpeting, floor mats, headliners, and trim moldings are next. Workers stretch and press these components into place using heat guns and hand rollers to ensure wrinkle-free surfaces and tight fits. The sunroof assembly is dropped in from above and sealed with multi-layer gaskets to prevent leaks. All the while, every stage includes quality inspections using both visual checks and functional tests. Is the stitching even? Does the infotainment system respond instantly to input? Is the rear seat heating element warming to spec? These aren't afterthoughts. They're checked and verified at every step. With the interior mostly complete, attention now turns to the installation of exterior finishing components. This includes the lighting systems, trim pieces, bumpers, grills, and the wheels and tires. Headlights and taillights are delivered in sealed packaging and installed using torque-controlled tools to avoid over-tightening. Each lighting unit is powered on and subjected to an alignment procedure that ensures optimal beam projection. The G-Class often includes LED matrix lighting, so precise calibration is required to ensure adaptive lighting functions correctly on the road. The bumpers, both front and rear, are more than decorative. They contain impact absorbers, parking sensors, and, in some models, radar modules for adaptive cruise control. These systems must be aligned with the vehicle's central ECU and tested for accuracy. The grille, which houses the iconic Mercedes three-pointed star, is mounted next, followed by trim pieces such as side skirts, fender flares, and the protective body cladding that's especially important for off-road variants. Wheels and tires are mounted towards the end of this phase. Each tire is balanced individually before mounting to minimize road vibration. The G-Class uses either 18-inch or larger wheels, depending on the model, and all are fitted with performance all-season or off-road tires. Lug nuts are torqued in a star pattern and then double-checked by a second technician for safety. The signature rear-mounted spare wheel is added last, requiring special reinforcement brackets to support its considerable weight. At this point, the vehicle is externally and internally complete, but it hasn't yet proven itself ready for the road. That's where the end-of-line testing begins. First, each vehicle is rolled onto a chassis dynamometer for a systems check. This stationary rolling road allows technicians to simulate driving conditions without the vehicle leaving the factory. Engines are started and revved through a range of RPMs. The transmission is cycled through its gears. Braking systems are tested under controlled load. Onboard diagnostics scan every system for fault codes, and calibration values are adjusted in real time. Next, the G-Class is taken into the water testing booth, a sealed chamber where high-pressure water jets blast the vehicle from all angles. This simulates heavy rainfall and river fording to confirm that all seals and gaskets are intact. Doors, windows, the sunroof, and even antenna mounts are tested for ingress. Any leaks are flagged for immediate remediation. Following the water test, vehicles are subjected to a visual inspection tunnel with multi-angle lighting. Here, inspectors walk around each unit, examining body panel gaps, paint reflections, wheel alignment, and emblem placement. Mirrors are adjusted, wiper blades tested, and final protective films removed. Finally, the G-Class is driven onto a short test track either inside or just outside the factory. This final road test includes a variety of surfaces: cobblestones, incline ramps, sharp turns, and slalom sections. Trained drivers listen for abnormal noises, feel for steering alignment, and evaluate ride quality. Any deviation from spec sends the vehicle to a special adjustment area for corrections. Only once all tests are passed does the vehicle receive its final factory seal of approval. Even then, however, the process isn't over. Depending on the destination, additional country-specific requirements are installed. These may include compliance labels, GPS regional settings, localized safety equipment, and left or right-hand drive adjustments. Paperwork is finalized, including the build sheet, quality inspection records, and shipment documentation. The vehicle is then either driven onto a covered transport truck or loaded into a sealed container for overseas shipping. Now that the G-Class has completed its rigorous in-factory birth, a process involving welding, painting, assembly, and exhaustive quality checks, it embarks on the next critical phase of its journey: preparation for global distribution. This phase, though less visually dramatic than robotic welders or precision-aligned dashboards, is nonetheless a feat of coordination and logistics. The moment a G-Class rolls out of the Magna Steyr facility in Graz, Austria, it transitions from handcrafted engineering marvel to a globally positioned product, bound for showrooms, private collections, mountain trails, or inner-city avenues. But before it reaches any of these, there is still a tremendous amount of effort that goes into protecting, staging, and transporting each unit with the same care and attention to detail used in its creation. Once a G-Class vehicle has passed its final road test and received its full quality release documentation, it is driven under its own power to the staging area adjacent to the main plant. Here, specially trained logistics personnel begin the final detailing and protection process. Although the vehicle is fully finished, there is a layer of preparation necessary to ensure it survives the rigors of global shipping. Protective films are applied to sensitive areas. The hood, roof, door sills, mirrors, and corners of the bumpers are covered with temporary plastic guards that resist scratches, UV exposure, and road grime. The alloy wheels are often wrapped in foam liners or protective rings to prevent damage from transport straps or accidental impacts during loading. Interior surfaces are also shielded with plastic covers over the seats, infotainment screens, and floor mats. Every vehicle is now tagged with a unique, VIN-linked logistics barcode, which details its destination, shipping method, port of entry, and delivery window. This data is integrated with Mercedes-Benz's global tracking system, allowing every stakeholder, from plant logistics to overseas dealerships, to monitor the car's location in real time. Depending on its final destination, the G-Class may undergo additional region-specific programming. For example, a vehicle bound for North America will be loaded with US-specific emissions calibrations and compliance documentation, while one heading to the Middle East might receive enhanced climate control settings and reinforced dust filtration for desert conditions. Next, the vehicle is routed to one of several outbound transport modes. For European customers or regional delivery, G-Classes are typically driven onto covered car haulers, large multi-deck trucks designed to transport 6 to 8 vehicles at a time. These trucks have air ride suspensions to reduce vibrations and protect the delicate ride height sensors and chassis calibration. For vehicles headed abroad, the process is more elaborate. The G-Classes are driven into rail cars or loaded into intermodal shipping containers, which are then routed to seaports like Bremerhaven in Germany or Koper in Slovenia. At the port, each container or open-deck vessel is handled with specialized cranes and ramps that minimize jostling. It is worth noting that many G-Class models, particularly Special Edition or G Manufaktur builds, are transported in sealed containers to prevent salt spray, sun fading, or theft. The voyage by sea can take several weeks. For example, vehicles headed to North America might pass through the English Channel, cross the Atlantic, and dock at ports like Baltimore or Brunswick. Once at port, they are processed through customs, emissions, and safety verification, all under the oversight of Mercedes-Benz regional distribution centers. Then comes a second round of quality control, sometimes called a PDI or pre-delivery inspection. This includes checking tire pressure, recalibrating navigation systems to the local GPS constellation, adjusting language and date formats, and inspecting the vehicle for any damage incurred during shipping. If a vehicle has traveled thousands of kilometers by rail, truck, and sea, this inspection is crucial to maintain the brand's reputation for perfection. Once cleared, the G-Class is dispatched to its final destination: a dealership, fleet customer, private buyer, or regional collection center. Even here, the aura of exclusivity surrounding the G-Class continues. Many buyers opt for specialized white glove delivery, wherein the vehicle is transported by single-car covered trailer and presented with ceremonial fanfare, unveiling cloth, branded key boxes, and sometimes a personal orientation session with a brand specialist. The delivery experience is designed to match the vehicle's pedigree, but beyond the logistics and visual pageantry, what truly makes the G-Class remarkable is that even after all of this effort, the vehicle is still, at heart, a rugged, off-road tool. Every single G-Class, whether destined for a downtown penthouse or a mining operation in Siberia, is built to the same foundational spec: full-time four-wheel drive, locking differentials, a 2-speed transfer case, and a ladder frame that could survive military deployment. That's the irony and the charm of the G-Class. It's capable of climbing a 45-degree incline, fording rivers, and navigating icy switchbacks, yet it will just as often be used to roll quietly over cobblestones in Monaco or park beneath luxury boutiques in Dubai. The factory doesn't know what fate awaits each G-Class, and it doesn't matter. Each one is engineered for extremes, regardless of how pampered its life may be. Now, let's take a moment to consider the people behind this machine. While many modern automotive factories are fully robotic and optimized for scale, the G-Class production line retains an unusually high proportion of human labor. Over 1,500 skilled workers at Magna Steyr contribute to its assembly, many of them having decades of experience with the model. Their knowledge, much of it gained through repetition, mentoring, and attention to the tactile feedback of materials, is irreplaceable. They know the right torque by feel. They can spot a millimeter-wide gap from across the room. In a time where artificial intelligence and robotics are reshaping the manufacturing landscape, the G-Class stands as an example of how artisanal skills still hold tremendous value. This blend of traditional craftsmanship and modern precision engineering is particularly evident in the G Manufacture program. Here, customers can personalize nearly every aspect of their G-Class, from more than 30 exterior paint killers to a wide range of leather hues, stitching patterns, interior trims, and wheel designs. If a buyer wants orange leather with green piping and a matte olive exterior, they can have it. These builds are not separated into another facility. They're integrated into the main production line with designated bays where craftsmen apply these one-off features by hand. This level of customization presents huge logistical challenges, matching materials to build slots, keeping non-standard parts in stock, and maintaining quality across thousands of permutations. Yet the factory has embraced this complexity as a way to deepen the bond between owner and vehicle. Meanwhile, let's not forget the rigorous quality control that continues to influence every element of the G-Class's construction. For example, every powertrain used in the G-Class, whether the twin turbocharged V8 in the AMG variant or the inline-6 in the standard model, undergoes cold testing prior to installation. In cold testing, engines are spun up using electric motors without firing them, while sensors measure oil pressure, bearing resistance, valve timing, and sealing. This ensures that only powertrains meeting exact tolerances make it to the assembly floor. Similarly, each differential assembly is bench tested for noise and balance before integration into the vehicle. It's not enough for components to fit. They must perform to exacting standards. Even paint color undergoes scientific scrutiny. After application, each painted body is checked using spectrophotometers, special instruments that detect even the slightest variation in hue, brightness, and saturation. This is especially important when replacing panels after damage or repair. Consistency in color across different batches of paint and lighting conditions is notoriously difficult. Yet, Mercedes insists on millimetric perfection, even for colors that might only be chosen by 1 in 1,000 customers. It's this obsessive attention to detail that makes the G-Class stand out, and it's why its production process is stretched over more than 100 hours per vehicle. Where other vehicles are designed for efficiency, the G-Class is designed for excellence. Every step, from welding to upholstery, from software calibration to final wheel alignment, is geared toward creating something more than just a car. It's a statement of what happens when engineering, tradition, and passion come together under one roof.